When most people think of the solar system, they picture the planets, the gas giants with their rings and storms, the rocky inner worlds with their familiar landscapes, or the sun blazing at the center. But in truth, the most intriguing stories, the strangest landscapes, and perhaps even the most promising havens for alien life, lie not on the planets, but on their moons. For decades, moons were thought of as passive companions, small spheres of ice and rock, locked in eternal orbit around their larger hosts, dim and unchanging. The moon was the archetype, airless, dead, grey, pockmarked by billions of years of impacts. If Earth's moon was typical, then surely the others must be the same. But the story turned out to be very different. The space age peeled back the curtain, and when spacecraft began to pass the outer planets, humanity's understanding of moons transformed forever. In the 1970s, the twin Voyager probes launched a revolution, sending back images that revealed volcanic worlds, cracked ice shells, sulfur-spewing geysers, and bizarrely sculpted surfaces. Later, the Galileo mission orbited Jupiter, showing us an ocean world hidden beneath Europa's icy skin. Cassini, the great Saturn orbiter, found a tiny world named Enceladus shooting jets of salty water into space, creating Saturn's E-ring and hinting at hydrothermal activity deep below. New horizons, rushing past Pluto, revealed a dwarf planet that was alive with glaciers, hazy skies, and nitrogen ice plains shaped like a beating heart. Even in the frozen reaches of Neptune, a lonely spacecraft once caught sight of Triton, a moon with geysers that defied the idea of lifelessness so far from the sun. Suddenly, the solar system's moons were no longer silent companions. They were active, dynamic, and in some cases, alive with chemistry that on Earth is linked with biology. They were not only weird, they were windows into the possible diversity of worlds across the galaxy. What Voyager, Galileo, Cassini, and New Horizons taught us is that planets may not be the only stage for life. Instead, the stage may just as well be set beneath thick ice shells, in methane seas, or in the sulfur-rich skies of worlds that are moons in name, but planets in every other respect. The imagination has always reached for the moons. Even before the spacecraft revealed them, writers and thinkers dreamed of them as alien realms. Johannes Kepler in the 17th century speculated about creatures living on Jupiter's moons, while Galileo himself, who first discovered Europa, Io, Ganymede, and Callisto in 1610, imagined them as other Earths. Much later, science fiction would claim Europa and Titan as the homes of strange intelligence or alien ecosystems, where human explorers were warned not to tread too heavily. Arthur C. Clarke's 2010 Odyssey 2 gave us the unforgettable line, "All these worlds are yours except Europa. Attempt no landing there." The idea that these distant moons might hold something sacred, something dangerous, or simply something precious has never left us. Yet the fascination is not only imaginative, it is scientific. In the last 50 years, astrobiology has emerged as a field, the search for life beyond Earth, whether microbial or intelligent. Moons have taken center stage in that story. Mars, with its dry valleys and ancient riverbeds, is still important. But Europa and Enceladus, Titan and Ganymede, even Triton and Pluto, have shifted attention outward, showing that oceans may be far more common than we once believed. In fact, if we counted only the volume of liquid water, Earth would not even be near the top of the list. Jupiter's moons alone may harbor far more water than our oceans combined. These hidden seas, kept warm not by sunlight, but by the flexing of gravity and the chemistry of hydrothermal vents, might be the best chance we have of finding extraterrestrial life in our cosmic backyard. To understand why these moons matter, we have to consider their diversity. Take Io, for example, a moon of fire, erupting with hundreds of active volcanoes, reshaping its surface constantly. A hellish landscape that looks more like Dante's Inferno than a place in our solar system. Or Titan, Saturn's great moon, wrapped in a thick atmosphere richer than Earth's, where rivers of methane flow and seas stretch for hundreds of kilometers, where dunes ripple in a frozen wind. Then there is Europa, smooth and white, cracked like stained glass, where astronomers imagine a black ocean filled with hydrothermal vents and the possibility of alien biology. Or Enceladus, small but spectacular, where water sprays into space, inviting spacecraft to fly through its plumes and taste its secrets. Some moons are oddly shaped, like Pan and Atlas, resembling ravioli drifting inside Saturn's rings. Others, like Iapetus, are split in half, one side dark as coal, the other bright as snow, with a great ridge running like a scar along its equator. And then there is Miranda, orbiting Uranus, where the surface seems stitched together from fragments of different worlds, a Frankenstein's patchwork of ice cliffs and grooves that defies neat explanation. This book is a journey into that strangeness. It is a voyage into the weirdest moons of the solar system, from the volcanic fury of Io to the methane seas of Titan, from the geysers of Enceladus to the frozen retrograde wanderings of Triton. It is a story about exploration, past, present, and future. We will follow the trail of the spacecraft that revealed these worlds and look ahead to the missions that will return. We will explore the possibilities of life and the new science that tells us moons might be the most likely places for biology to emerge in the galaxy. And we will marvel at the ways in which moons remind us that the universe is stranger, richer, and more imaginative than we could have dreamed. What sets moons apart is not only their strangeness, but also their intimacy. They orbit close to their planets, caught in gravitational embraces that twist and heat them, shaping their geology and chemistry. Planets dominate by sheer mass, but moons are laboratories of complexity. Tidal forces turn them into engines, creating volcanoes on Io, oceans on Europa, and geysers on Enceladus. Where planets settle into predictable orbits, moons dance in resonances, tugging at each other, exchanging energy. And while planets carry atmospheres or magnetospheres, moons are often the source of them. Enceladus, for instance, creates Saturn's E-ring with its icy sprays. Io fills Jupiter's magnetic field with sulfur and plasma. Titan's atmosphere, thicker than ours, is a miniature planet in itself, defying the vacuum around it. In many ways, moons are microcosms of the solar system. They display all its possible environments, compressed into small packages: volcanic, icy, oceanic, atmospheric. Some mimic Earth in strange ways, offering analogues of rivers, lakes, and weather, though with different materials like methane instead of water. Others offer visions of extremes that Earth never knew. Heat so intense it erases impact craters. Cold so deep it preserves ancient scars untouched for billions of years. To study moons is to study diversity, to learn what the cosmos can create when given gravity, chemistry, and time. Exploration of moons is also exploration of ourselves. Every mission that has traveled outward has revealed something that makes us question our assumptions. Cassini's last plunge into Saturn in 2017 was not only a scientific end, but also a symbolic one. A reminder that we had only just begun to touch these worlds. The upcoming Europa Clipper will carry cameras, radar, and instruments to peer into Europa's ice. JUICE, the European mission, will orbit Ganymede and study Jupiter's ocean worlds in detail. Dragonfly, perhaps the most ambitious of all, will fly across Titan's landscape. A nuclear-powered drone exploring dunes and lakes, like a science fiction dream come true. These missions are not abstract. They are steps in humanity's journey outward, steps toward understanding what it means to be alive in the universe. If life exists in Europa's ocean, or in Titan's methane chemistry, it will change not only science, but also philosophy and religion, art and imagination. It will answer the question that has haunted us for centuries: are we alone? And even if life is absent, the moons are still treasures, places of beauty and mystery that remind us how fragile and unique Earth is, and yet how full the universe might be of surprises. As we begin this exploration in these pages, keep in mind that every moon tells a story. Some stories are violent, some are quiet, some are eerie in their silence, and some are active, chaotic, and alive with movement. Together they form a chorus of worlds that orbit in darkness, reflecting sunlight and human curiosity alike. They are reminders that the solar system is not a set of tidy orbits, but a vast family of diverse and unpredictable members. Planets may dominate, but moons tell the secrets. This introduction, then, is an invitation. The chapters ahead will take you through the frozen seas of Europa, the firestorms of Io, the methane clouds of Titan, the alien plumes of Enceladus, and the forgotten fringes of Pluto, Charon, and Triton. Along the way, we will see how missions have transformed knowledge into wonder, how science fiction has often foreshadowed discovery, and how astrobiology has placed moons at the forefront of the search for life. The solar system is weirder than we once thought, and the moons are its strangest citizens. Europa, the ocean beneath the ice. The first real close-ups came from the Voyager missions in 1979. Voyager 1 and 2 swept past Jupiter and sent back grainy but revolutionary images. Europa's icy surface glowed pale and enigmatic, crossed by dark lines that looked like a web of veins, or the cracks in broken glass. Scientists were baffled. What could cause such patterns? Why was the surface so fresh and bright? The Voyagers gave only a tantalizing glimpse, but they left questions that demanded answers. Those answers began to take shape with the Galileo spacecraft in the 1990s. Launched in 1989 and arriving at Jupiter in 1995, Galileo carried cameras and instruments capable of mapping Europa in detail. The images it sent back were astonishing. Europa's surface was a frozen canvas, painted with chaotic terrain. Ridges, bands, and disrupted areas where ice plates appeared to have broken apart and shifted, as though floating on a liquid beneath. It was as if Europa were an Arctic world with a crust of sea ice drifting atop a vast ocean. This was no dead moon. It was a world with activity, a world alive with motion beneath its frozen skin. The idea of a subsurface ocean took root. Galileo's magnetometer detected variations in Jupiter's magnetic field near Europa, which could be explained if a salty, electrically conductive ocean lay beneath the ice. The surface, features themselves suggested movement. Bands where new ice had welled up. Chaos regions where blocks had rotated and shifted like icebergs trapped in pack ice. Impact craters, which might have punctured the crust, were rare and shallow, further hinting at a pliable, mobile surface. Altogether, the evidence pointed to a vast hidden ocean, sealed away under perhaps 10 to 20 kilometers of ice, and containing more water than all of Earth's oceans combined. The implications were staggering. On Earth, wherever liquid water exists, life seems to follow. In deserts, in boiling hot springs, even at the bottom of the ocean near hydrothermal vents. If Europa had a global ocean, warmed by the flexing tides of Jupiter's gravity, it might also have the ingredients for life. Hydrothermal vents at the seafloor could provide energy and nutrients, just as they do on Earth. Microbes could flourish there, perhaps even more complex organisms. The smooth, cracked ice we see from above might conceal a biosphere more alien and more fascinating than anything yet discovered. Europa became a symbol of possibility. Scientists, writers, and the public alike began to imagine what might swim in its darkness. Would it be microbes, invisible to the human eye? Or strange multicellular creatures adapted to the crushing pressure and eternal night? The ocean might be sterile, but it might also be teeming. And if life had arisen independently on Europa, then the universe might be full of life, because it would mean life is not a rare accident, but a natural consequence of chemistry and energy wherever water exists. The Galileo images also revealed Europa's haunting beauty. Its surface, with red-brown streaks crossing a bright white plain, looked like an abstract painting, alien, yet strangely familiar. Scientists debated the composition of those streaks. Perhaps salts, perhaps sulfur compounds carried upward from the ocean. In some regions, the ice appeared broken and jumbled, frozen chaos where the crust had been disrupted by forces below. These regions looked like frozen seas in the Arctic after a storm, where the ice has fractured and refrozen into a jagged puzzle. The idea that similar processes might be happening on a moon nearly 500 million miles away was breathtaking. But the Galileo mission also highlighted the limits of our exploration. Its instruments were limited, and radiation from Jupiter's magnetic field damaged its electronics over time. The spacecraft provided hints, strong hints, but not proof. The existence of an ocean remained an inference, not a direct observation. What Galileo did accomplish was to transform Europa from a curiosity into one of the prime targets for astrobiology. It left behind a mystery, one that future missions would have to unravel. Europa also became a touchstone in science fiction. Arthur C. Clarke had imagined it even before Galileo, warning humanity not to disturb its waters in 2010, Odyssey 2. The notion that Europa might harbor a fragile, nascent ecosystem took root in the collective imagination. Films, novels, and games returned again and again to the moon, treating it as a stage for alien life or human exploration. In this way, Europa straddled the line between science and imagination, embodying both the rigorous evidence of spacecraft and the limitless speculation of art. The fascination is partly because Europa feels both alien and familiar. It is not as grotesquely strange as Io's sulfur eruptions or as exotic as Titan's methane seas. Instead, it looks like Earth's polar regions, only on a global scale, and underlain by mysteries we can scarcely touch. That familiarity makes the possibility of life more tangible. Standing on Europa's surface, if one could withstand the radiation and cold, one would see a stark landscape of ice, ridges stretching for kilometers, a horizon of pale plains. Above, Jupiter would loom enormous, its bands and storms visible in detail, rising and setting in slow grandeur as Europa orbited. It would be alien, but it would also echo Earth's own frozen places, a reminder that the cosmos often rhymes even in its strangeness. The first glimpses of Europa, then, were not only a scientific revelation, but also a philosophical one. Here was a small world, smaller than Earth's moon, orbiting a giant planet, yet it might contain an ocean vaster than ours. Here was proof that habitability is not limited to planets in the Goldilocks zone of a star. Life might find a way not by basking in sunlight, but by drawing warmth from the tides of gravity and the chemistry of rock and water. Europa shifted the goalposts. It suggested that habitable worlds might be everywhere, hidden beneath ice shells in the far reaches of space. Galileo. The man could never have imagined such details when he first saw his little points of light in 1610. But perhaps he sensed, dimly, that they meant something larger, that the universe was richer than humanity had believed. 400 years later, with spacecraft and science, we are beginning to grasp what those lights truly are. worlds as strange and varied as anything on Earth, and Europa above all as one of the most compelling. The first glimpses from Voyager and Galileo have given us a portrait of a world poised between silence and potential, a world waiting to tell its story. The case for an ocean. When scientists speak about Europa today, the conversation almost always circles back to the same point. The ocean. It is not the streaks, nor the smoothness of the surface alone, nor even the strange chemistry of its cracked plains that capture attention. It is the idea that beneath that icy crust lies an ocean of liquid water, a true sea that encircles the moon entirely. This idea has transformed Europa from a frozen outpost into one of the most compelling destinations in the search for life. But how do we know that such an ocean exists when no human or machine has yet drilled through the ice? The answer lies in a chain of evidence, drawn from spacecraft instruments, orbital mechanics, and the language of geology translated across nearly 500 million miles. The story begins with Europa's orbit itself. Unlike Earth's moon, which is locked into a near-perfectly circular orbit, Europa's path around Jupiter is slightly elliptical. That eccentricity means Europa is constantly pulled and released by Jupiter's immense gravity. Every orbit, it is flexed like a rubber ball being squeezed and stretched. The internal friction caused by this gravitational tug-of-war generates heat, a process known as tidal heating. This same mechanism is what powers the volcanic fury of Io, which lies closer to Jupiter. But in Europa's case, the heat is gentler, spread through a world of ice and rock. Without tidal heating, Europa would be a frozen block, its water solid from surface to core. With it, there is enough warmth to keep a global ocean liquid beneath the shell. Voyager's flyby hinted at this possibility, but it was Galileo that made the case. Its images revealed a surface fractured into ridges and bands, as if the crust were floating and shifting atop something mobile. These bands resembled Earth's mid-ocean ridges, where molten material wells up and pushes the seafloor apart. Some of Europa's features looked eerily similar. Lines of darker material, tens of kilometers wide, where ice plates had separated, and fresh ice had frozen in between. The resemblance was not proof, but it was strongly suggestive. More dramatic still were the chaos terrains. Galileo's cameras showed regions where the surface looked as though it had been shattered and then frozen again. Blocks of ice, some the size of cities, appeared rotated and displaced, locked into place in a jumbled mosaic. Scientists likened it to a giant jigsaw puzzle that had been scrambled. The most plausible explanation was that warm water or slushy ice had risen from below, melting or softening the crust and allowing the plates to drift before refreezing. These chaos terrains were unlike anything seen on the Moon, Mars, or Mercury. They demanded an explanation that included liquid beneath the surface. Then came the magnetic evidence. Galileo carried a magnetometer, an instrument designed to measure magnetic fields. When the spacecraft passed near Europa, it detected strange fluctuations in Jupiter's magnetic environment. The best explanation was that a conductive layer lay beneath the surface of the Moon. Salt water, rich in dissolved minerals, conducts electricity and would interact with Jupiter's magnetic field in precisely the way Galileo observed. This was a powerful clue. Not only did Europa likely have water, but it was salty, an ocean closer to Earth's seas than to a sterile reservoir. Enceladus, the geyser world. For most of human history, Enceladus was nothing more than a faint point of light, an afterthought among Saturn's dozens of moons. Discovered in 1789 by William Herschel, it measured barely 500 kilometers across. Small enough that many assumed it would be geologically dead, a frozen relic too tiny to retain heat or activity. Compared to the grandeur of Titan with its thick atmosphere, or the enigmatic Iapetus with its yin-yang surface, Enceladus seemed unremarkable. Astronomers catalogued it, gave it a name from Greek mythology, and moved on. For more than 2 centuries it lurked in obscurity, circling Saturn unnoticed. That obscurity ended in 2005, when a spacecraft named Cassini turned its cameras toward Enceladus and saw something extraordinary. Cassini had been launched in 1997, a joint NASA-ESA mission designed to study Saturn and its system in unparalleled detail. When it arrived in 2004, the spacecraft quickly became a window into a realm of wonders. Saturn's rings, Titan's methane lakes, storms larger than Earth, and the behavior of dozens of moons. But among all these discoveries, Enceladus emerged as the most shocking. Cassini's first flybys of Enceladus were routine. The tiny moon gleamed white, its surface highly reflective, suggesting fresh ice. Its terrain was varied, some regions smooth and young, others cratered and ancient. It was intriguing, but nothing prepared scientists for what came next. In March 2005, as Cassini made a close pass, its instruments detected something strange. The spacecraft flew through a cloud of particles, icy grains that seemed to be emanating from the moon itself. Images soon confirmed the source: geysers of water vapor erupting from Enceladus's south pole, shooting hundreds of kilometers into space. The sight was astonishing. Plumes streamed out from long fissures later nicknamed the tiger stripes. These geysers were not small. They were colossal fountains, jetting material into Saturn's orbit, creating the planet's faint E-ring. No one had expected such activity from such a small body. It was as if Enceladus, once dismissed as insignificant, had stood up and declared itself one of the most dynamic worlds in the solar system. The discovery electrified the scientific community. Water vapor meant water, and where water exists, the possibility of habitability follows. Cassini's instruments went to work, analyzing the composition of the plumes. They detected salts, suggesting that the water came not from surface ice, but from a liquid ocean beneath. They found organic molecules, the building blocks of life. They even measured tiny silica particles, hinting at hydrothermal activity. Hot water reacting with rock, just as in Earth's seafloor vents. In a single stroke, Enceladus vaulted from obscurity to the front lines of astrobiology. What made the discovery all the more remarkable was that Enceladus should not, by all expectations, have been active. Its small size means it should have cooled long ago, its interior frozen solid. And yet, tidal forces from Saturn and interactions with other moons supply just enough energy to keep water liquid beneath the crust. This delicate balance makes Enceladus a paradox: tiny, fragile, yet alive with activity that rivals worlds much larger. The images Cassini sent back were hauntingly beautiful. Against the blackness of space, Enceladus's south pole glowed with faint blue jets, illuminated by sunlight. The tiger stripes stretched for hundreds of kilometers, glowing faintly in thermal images, each fissure a source of geysers. The plumes themselves formed shimmering curtains, composed of countless jets merging into a fountain that extended far above the surface. To watch these eruptions was to see a world breathing, exhaling its secrets into space. The surprise was not only visual. Cassini's instruments could taste the plumes directly, flying through them on repeated passes. Mass spectrometers detected water vapor, carbon dioxide, methane, ammonia, and a variety of organics. Salt grains pointed to a connection with a global subsurface ocean in contact with rock. The conclusion was inescapable. Beneath its icy shell, Enceladus harbors a warm, salty ocean, one that may be one of the most habitable places in the solar system. For planetary scientists, the implications were enormous. Enceladus offered direct access to an alien ocean. Unlike Europa, with its thick shell and uncertain plumes, Enceladus was actively ejecting ocean material into space. A spacecraft could literally fly through the spray and analyze its chemistry, no drilling required. This was a gift beyond expectation, a natural pipeline from an alien sea to space. The excitement extended beyond science. Enceladus became a cultural phenomenon, a symbol of hidden wonders waiting to be found. Artists depicted its geysers as glowing fountains. Science communicators called it a cosmic snow globe. Astrobiologists speculated openly about the potential for microbial life, perhaps thriving near hydrothermal vents in its ocean. Suddenly, a moon no larger than England was sharing headlines with Mars, Europa, and Titan as a prime target in the search for life. Cassini continued to make passes over Enceladus for more than a decade, refining our knowledge. Each encounter confirmed the vitality of the plumes, their persistence, and their complexity. In 2015, Cassini made its closest flyby, diving just 50 kilometers above the surface, directly through the jets. It tasted molecular hydrogen, a byproduct of hydrothermal reactions. On Earth, microbes use hydrogen as an energy source, forming the base of chemosynthetic ecosystems. The detection of hydrogen on Enceladus was one of the strongest hints yet that its ocean could be habitable. Scientists began to speak of Enceladus not as a maybe, but as a strong candidate for life. The ingredients checklist seemed to be filled: liquid water, organics, energy sources, hydrothermal chemistry. Everything necessary for biology, as we understand it, appeared to be present. The only missing piece was direct evidence of life itself. Cassini lacked the instruments to detect microbes definitively, but the hints it gathered set the stage for future missions. Looking back, Cassini's surprise was not just that Enceladus had plumes, but that those plumes told such a rich story. They revealed a moon far more complex than size would suggest, a world that defies assumptions about what is possible in the solar system. Enceladus taught us that small does not mean dead, and that habitable environments may exist in the most unlikely places. It also underscored the importance of exploration. No telescope from Earth could have seen the geysers. No theory had predicted them. Only by sending a spacecraft, by daring to go and look, did humanity uncover this marvel. Enceladus reminds us that the universe holds surprises we cannot anticipate, and that sometimes the smallest worlds contain the biggest revelations. Today, Enceladus is no longer obscure. It is iconic. Its name evokes images of icy fountains, hidden oceans, and alien possibilities. Cassini's big surprise transformed it from a footnote in Saturn's catalogue into a central character in the story of life beyond Earth. And as future missions are planned, scientists know one thing for certain: we must return. The world that breathed secrets into space still has much to tell us, and the stakes of listening could not be higher. When Cassini first dipped its instruments into the icy breath of Enceladus, the question was not simply what is there, but what does it mean? The geysers erupting from the moon's south pole were a spectacle in themselves, a revelation that Enceladus was active, alive with geological processes. But what mattered most was their composition. To scientists, the plumes were more than fountains of ice. They were samples of an alien ocean, delivered freely into space. Cassini, with its suite of spectrometers and detectors, was in the perfect position to catch and analyze these gifts. What it found would transform Enceladus from a curiosity into a serious contender in the search for life. The first surprise was salt. Early analysis showed that the ice grains in the plumes contained sodium and potassium salts, the same minerals found dissolved in Earth's oceans. This was significant because it implied that the plumes were not simply surface frost blasted into space, but rather ocean water that had interacted with the rocky seafloor. Salt water meant chemistry, and chemistry meant complexity. A sterile ice layer, uncontaminated by rock, would have little to offer life. But water in contact with minerals can leach nutrients, create redox gradients, and provide the foundation for biological processes. The salts in the plumes were the first clue that Enceladus's ocean might be not just liquid, but alive with chemical possibilities. Then came organics. Cassini's mass spectrometers detected carbon-bearing molecules, methane, carbon dioxide, and a range of simple organics. These molecules are the scaffolding upon which life is built. On Earth, methane is often associated with biological activity, though it can also form abiotically. Carbon dioxide is central to many metabolic processes. Even more tantalizing were later detections of larger, more complex organics, some with molecular masses hundreds of times greater than methane. These heavy organics suggested that complex chemistry was occurring within the ocean, potentially akin to the prebiotic chemistry that once seeded life on Earth. Perhaps the most decisive finding came in 2017, more than a decade into Cassini's mission. As the spacecraft dove through the plumes one last time, its instruments detected molecular hydrogen, H2, streaming from the vents. On Earth, molecular hydrogen is a key energy source for microbes at hydrothermal vents. It is produced when hot water interacts with rock in a process called serpentinization, where minerals like olivine react with water to form new minerals and release hydrogen. That hydrogen then becomes food for microbes, which oxidize it to create energy. The presence of hydrogen on Enceladus was therefore a smoking gun for hydrothermal activity. It suggested not only that an ocean existed, but that it was chemically active, with energy sources capable of sustaining life. To astrobiologists, the checklist was filling itself out. Water, check organics, check energy sources, check hydrothermal activity, check saltwater contact with rock, check Enceladus, a tiny moon no larger than the British Isles, had somehow vaulted to the top tier of habitable environments in the solar system. Suddenly, the conversation shifted from whether Enceladus might be interesting to whether it might already be alive. The chemistry of the jets also provided a glimpse into the dynamics of the hidden ocean. The presence of salts and organics indicated circulation between the ocean and the seafloor. The detection of silica nanoparticles pointed to water heated to at least 90 degrees Celsius, hot enough for robust hydrothermal systems. Together, these findings painted a picture not of a stagnant reservoir, but of a dynamic, geologically active ocean. Warm water, minerals, and organics cycling through vents and fissures. These are the ingredients that made Earth's early oceans fertile ground for life's emergence. The fact that these discoveries came from plumes was almost miraculous. Unlike Europa, where thick ice may guard the ocean jealously, Enceladus seemed eager to share. The tiger stripes at its south pole function like natural pipelines, channeling ocean water to the surface and spraying it into space. For scientists, this was a gift beyond measure. Instead of designing impossibly complex drills to bore through kilometers of ice, they could fly a spacecraft directly through the spray and let the moon deliver samples itself. It was as if Enceladus were holding out a glass of water to be tested, saying, "Here, see what you find." Not all scientists agree on the implications. Some argue that the presence of organics does not necessarily indicate life, only chemistry. Methane, for example, can be produced abiotically through serpentinization, as well as by microbes. Complex organics can form in hydrothermal systems without biology. The detection of hydrogen, while exciting, is not proof of microbial activity. In other words, Enceladus checks the boxes for habitability, but not for life itself. The difference is crucial. It tells us the stage is set, but not whether the actors have arrived. And yet the parallels with Earth are difficult to ignore. On our planet, life flourishes in precisely the conditions inferred on Enceladus. Hydrothermal vents teem with microbes, tube worms, clams, and crabs, all feeding off chemosynthetic ecosystems. The analogy is so strong that it feels almost perverse to imagine Enceladus's ocean lying empty. If it has water, organics, energy, and geochemistry, why would life not emerge there too? Perhaps it has. Perhaps it still thrives, unseen in the darkness. The astrobiological stakes are profound. If life is found on Enceladus, it will almost certainly have arisen independently from Earth. The distance is too great, the isolation too complete for contamination to explain it. That would mean two origins of life in one solar system. Proof that biology is not a cosmic fluke, but a natural outcome of chemistry wherever conditions allow. It would be the most significant scientific discovery in human history. And the evidence begins with salts, organics, and hydrogen, tiny signatures in the chemistry of jets. The plumes also hold lessons for planetary science. They remind us that small worlds can be surprisingly active, and that the boundaries of habitability are far broader than once thought. Enceladus, barely 1/40th the diameter of Earth, should by all rights be geologically frozen. Instead, tidal heating has kept its ocean liquid for billions of years. If such a world can sustain habitability, then how many others exist, orbiting giant planets around distant stars? Every exoplanet system we discover may harbor not just planets, but moons like Enceladus, each with oceans and chemistry waiting to be explored. Culturally, the chemistry of the jets has given Enceladus an identity. It is no longer just a small icy moon. It is the geyser world, the snow-white fountain of Saturn. Its jets inspire artists and filmmakers. Its chemistry inspires astrobiologists. And its beauty inspires anyone who sees the images of shimmering plumes against the darkness of space. Enceladus is a reminder that the universe does not reveal its treasures only in grand scales. Sometimes, the smallest worlds hold the richest secrets. As Cassini plunged into Saturn's atmosphere in 2017, ending its mission, it left behind more questions than answers. We now know that Enceladus has a global ocean, complex chemistry, and hydrothermal activity. But we do not know if life has taken hold there. To find out, we must return. The next mission to Enceladus will almost certainly carry more advanced mass spectrometers, capable of detecting complex biosignatures, amino acids, lipids, perhaps even cells themselves. And because the plumes are still active, those signatures may be waiting in the spray, ready to be captured. The chemistry of Enceladus's jets, then, is more than data. It is a message. It tells us that a tiny moon, once overlooked, harbors conditions strikingly similar to the ones that gave rise to life on Earth. It whispers that biology might not be unique, that chemistry strives toward complexity wherever water and energy meet. And it challenges us, urging us to return, to sample more deeply, to dare to ask the question outright, are we alone? When Cassini revealed Enceladus's geysers, the question quickly followed. How could such a tiny world sustain such activity? At just 500 kilometers in diameter, Enceladus should have frozen solid billions of years ago. Its heat should have long since leaked into space, leaving it inert, as cold and lifeless as most small moons. And yet geysers of liquid water vapor, organics and salts, spew from its south pole, replenishing Saturn's E-ring, hinting at an ocean beneath. To understand this paradox, we must examine the strange interplay of gravity, geology, and heat, forces that turn a tiny, icy moon into one of the solar system's most dynamic worlds. The answer begins with tidal heating. Enceladus is locked in a gravitational dance with Saturn and its neighboring moon Dione. This dance keeps Enceladus's orbit slightly elliptical rather than perfectly circular. As it moves closer to Saturn, the giant planet's immense gravity stretches Enceladus, flexing its interior like a rubber ball. As it moves farther away, the tension relaxes. This constant squeezing and stretching generates internal friction, which in turn produces heat. On Earth, friction from tectonic movements releases energy in earthquakes. On Enceladus, it releases energy as heat inside the ice and rock. This heat is not enough to melt the entire moon, but it is enough to keep vast reservoirs of liquid water beneath the surface. We can think of Enceladus as a cosmic pressure cooker. Beneath a relatively thin ice shell, perhaps 20 to 30 kilometers thick at the equator, and as little as a few kilometers near the South Pole, lies a global ocean, tens of kilometers deep. Below that ocean, a rocky core provides a seafloor where water meets minerals. Tidal heating is concentrated especially in the core, where friction and deformation generate warmth. Models suggest that this heating could drive hydrothermal activity, with hot water circulating through porous rock and erupting at vents into the ocean. This scenario neatly explains Cassini's detection of hydrogen gas in the plumes, a hallmark of water-rock interaction. The localization of the geysers at the South Pole is another clue. Why not across the entire moon? Thermal models suggest that the ice shell is thinner there, where heat is focused by the tidal stresses. The tiger stripes, those 4 great fissures crisscrossing the pole, act as weak points, where ocean water can seep upward, depressurize and explode outward as plumes. It is as if the South Pole is a safety valve, releasing pressure from the ocean below. Without tidal heating, the ice would thicken and seal, the geysers would shut down, and Enceladus would fall silent. With it, the moon becomes a fountain, constantly exhaling water vapor into space. The magnitude of this heating is remarkable. Cassini's infrared instruments revealed that the tiger stripes are far warmer than their surroundings, glowing faintly with heat despite the frigid surface temperature of -200 degrees Celsius. The fissures themselves can reach -75 degrees Celsius, still freezing, but hundreds of degrees warmer than expected. That warmth is the fingerprint of tidal heating at work. Evidence that Enceladus is not in thermal equilibrium, but in constant flux. Hydrothermal heat is crucial not only for keeping water liquid, but also for enabling chemistry. When water circulates through hot rock, it dissolves minerals, releases gases like hydrogen and methane, and creates chemical disequilibria, the very imbalances that life exploits for energy. On Earth, hydrothermal vents teem with chemosynthetic microbes, which oxidize hydrogen and sulfide to build organic matter. If Enceladus's ocean floor hosts similar vents, they could provide energy-rich habitats where alien microbes might thrive. The detection of hydrogen in the plumes strongly supports this possibility, pointing to active vent systems beneath the ice. The idea of hydrothermal circulation also helps explain Cassini's discovery of silica nanoparticles in the plumes. On Earth, such particles form when very hot water, over 90 degrees Celsius, interacts with rock, and then cools as it rises. The presence of silica grains in Enceladus's jets implies that water is being heated to high temperatures at depth, and then expelled upward. This is a powerful confirmation that hydrothermal systems exist on the seafloor. For astrobiologists, it is perhaps the most tantalizing evidence yet, direct proof that Enceladus has the very same processes that make Earth's deep oceans habitable. Enceladus's heat is sustained not only by its eccentric orbit, but also by orbital resonance. Locked in a 2-to-1 resonance with Dione, Enceladus's orbit is constantly being nudged, preventing it from circularizing. Without that resonance, its orbit would gradually settle into a perfect circle. Tidal stresses would diminish, and the heat would fade. Instead, the gravitational tug-of-war keeps the eccentricity alive, the flexing continuous, and the ocean liquid. This delicate balance, Saturn's gravity, Dion's nudges, Enceladus's orbit, maintains the conditions for activity over billions of years. It is a cosmic choreography, finely tuned, that turns a tiny moon into a hydrothermal world. Some researchers speculate that the heating is not evenly distributed, but concentrated in pockets, leading to variability in the plumes. Cassini observed changes in plume intensity over time, suggesting that the fissures open and close, depending on tidal cycles. When Enceladus is closest to Saturn, tidal stresses stretch the crust, widening the cracks and increasing plume activity. When it is farther away, the fissures tighten, reducing the output. In this way, Enceladus breathes with its orbit, its geysers pulsing in rhythm with Saturn's gravity. Hydrothermal heat also explains why the ocean remains stable, despite Enceladus's small size. A body of water so vast should freeze over geological timescales, but the constant input of heat keeps it liquid. Some models even suggest that the ocean could have persisted for billions of years, providing an unbroken environment for potential life to arise and evolve. Unlike temporary lakes or transient habitats, Enceladus's ocean may be a long-lived cradle, enduring long enough for biology to take root. The paradox of Enceladus is that such a small world can host such complexity. Its gravity is weak, its atmosphere non-existent, its surface temperature unimaginably cold. By all accounts, it should be inert. And yet, deep inside, it hosts warmth, circulation, and chemistry. This inversion of expectations reshapes our vision of the solar system. Habitability does not scale with size. Even the tiniest moons can surprise us. If Enceladus can harbor hydrothermal oceans, then similar worlds may abound, orbiting not only Saturn but exoplanets across the galaxy. Hydrothermal heat, then, is more than a curiosity. It is the engine that powers Enceladus's geysers, the force that sustains its ocean, and the reason why it has become a prime target in the search for life. Without it, Enceladus would be just another icy moon, forgotten in Saturn's shadow. With it, Enceladus is transformed into a world of possibility, where the conditions that once nurtured Earth's earliest microbes may be mirrored on an alien seafloor. In the end, the story of Enceladus is a reminder that life requires not just water, but dynamism. Stagnant water may persist for a time, but without energy, without heat, it cannot sustain the cycles of chemistry that make biology possible. Hydrothermal systems provide that spark, endlessly renewing, endlessly driving reactions. They turn oceans into laboratories, and on Enceladus, they may have turned a tiny moon into one of the most habitable places in the solar system. When Cassini first spotted the fountains of Enceladus, the realization was immediate. Here was a moon flinging pieces of itself into space, freely offering samples of its hidden interior. For planetary exploration, this was an extraordinary gift. Normally, the search for subsurface oceans conjures images of impossible engineering feats. Drills boring through kilometers of ice, probes descending into black waters. But Enceladus spared us that challenge. It was already venting its secrets into the vacuum, creating a natural highway from ocean to space. All we had to do was fly through the spray and taste it. And so, Cassini did. On multiple occasions, The spacecraft adjusted its trajectory to pass directly through the plumes at the South Pole. Imagine the audacity of the maneuver. A probe traveling tens of thousands of kilometers per hour, threading itself through geysers hundreds of kilometers high, dodging icy grains while keeping its instruments wide open. Cassini became, in effect, the first interplanetary sampler. An explorer not merely looking from afar, but literally inhaling the breath of another world. The instruments that made this possible were designed long before anyone imagined Enceladus would be erupting. Yet by happy coincidence, they were perfectly suited to the task. The Ion and Neutral Mass Spectrometer, INMS, could analyze gases, sniffing out water vapor, methane, ammonia, and carbon dioxide. The Cosmic Dust Analyzer, CDA, could measure the mass and composition of microscopic ice grains striking its detectors. Together, these instruments transformed Cassini into both chemist and geologist, dissecting the plumes molecule by molecule. What they revealed was astonishing. The plumes were composed primarily of water vapor, confirming that liquid lay beneath the surface. But mixed into that water were salts, sodium, potassium, and carbonates. Unmistakable signatures of ocean water in contact with rock. The CDA even found that some grains contained salts encased in icy shells, tiny frozen droplets of seawater. In essence, Cassini had caught sprays of alien brine, the chemical fingerprint of an ocean not unlike Earth's. The INMS delivered further revelations. Flying through the plumes at altitudes as low as 50 kilometers, it detected not just water vapor, but methane, carbon dioxide, and ammonia. These molecules hinted at complex geochemistry within the ocean. Methane was particularly intriguing because of its ambiguous origin. On Earth, it can be produced abiotically in hydrothermal reactions, but it is also a common byproduct of microbial metabolism. The question immediately arose, was Enceladus producing methane through geology alone, or could life be involved? Cassini could not answer, but it raised the stakes immeasurably. Even more remarkable was the discovery of molecular hydrogen. During its closest flybys, Cassini detected H2, streaming from the plumes in significant quantities. This was a smoking gun for hydrothermal activity. On Earth, hydrogen is produced when seawater reacts with certain minerals at high temperatures in a process called serpentinization. At hydrothermal vents, microbes feed on that hydrogen, using it as a primary energy source. The presence of hydrogen on Enceladus strongly suggested that similar reactions were taking place on its ocean floor. For astrobiologists, this was a thrilling moment. One of the clearest indicators yet that Enceladus is not just habitable in theory, but actively generating the chemical energy life requires. The discoveries did not end there. Cassini's instruments detected complex organic molecules, far larger than simple methane or carbon dioxide. Some had masses of over 200 atomic units, implying chains of carbon atoms and functional groups. The kinds of molecules that form the scaffolding of cell membranes and other biological structures. These were not the full complexity of life, but they were far beyond the simplest chemistry. The ocean of Enceladus was evidently capable of producing or sustaining prebiotic compounds, pushing it even closer to the threshold of biology. Flying through the plumes was not without risk. The icy grains, though microscopic, struck the spacecraft at relative speeds of several kilometers per second. They could damage instruments or surfaces. Yet Cassini weathered the encounters, absorbing the impacts and turning them into data. Each grain that hit the CDA became a messenger from the depths, carrying stories of salts, silicates, and organics. Each molecule captured by the INMS was another clue to the ocean's chemistry. In the end, Cassini's daring flights transformed Enceladus from a mysterious moon into one of the most thoroughly studied ocean worlds in the solar system. Perhaps the most poetic aspect of these flybys was their immediacy. For the first time, humanity had tasted another ocean. Not with lips or tongues, but with instruments built by human hands, flung across the void, drinking in the spray of a distant world. The idea that alien seawater had struck our machines, frozen brine grains crashing into sensors, is staggering. Somewhere beneath Enceladus's crust, water circulated through rock, dissolved minerals, built organics, and then erupted into space where our spacecraft caught it. The gap between Earth and alien seas had never been narrower. Scientists have since pored over the data, debating their implications. Some argue that the methane levels detected cannot be explained solely by abiotic processes, suggesting possible biological sources. Others counter that exotic geochemistry could suffice. Models have been built to simulate Enceladus's ocean chemistry, testing whether life is needed to account for the observations. The debate remains unresolved, but the fact that such a debate even exists is remarkable. A tiny moon once deemed uninteresting is now the subject of one of the most profound scientific questions imaginable. Cassini's sampling of the plumes has also shaped future mission concepts. Proposals like the Enceladus Life Finder, ELF, or Enceladus Orbilander envision spacecraft equipped with next-generation mass spectrometers, capable of detecting amino acids, lipids, or even whole cells in the plume particles. Unlike Cassini, which was never designed to detect life, these missions would explicitly search for biosignatures. And because the plumes are ongoing and accessible, such missions could be done without drilling or landing, a relatively low-cost, high-reward strategy. The plumes also provide a model for exploration beyond Enceladus. They suggest that other icy moons with subsurface oceans might also vent material into space, even if faintly. Europa may have plumes, though less dramatic than Enceladus's. Triton could erupt as well. If so, flyby sampling becomes a powerful tool in the astrobiologist's kit, a way of exploring hidden oceans without ever breaching their ice. In this sense, Enceladus is not just a moon, but a paradigm, showing us how to explore ocean worlds across the cosmos. For all its revelations, Cassini's plume sampling left us with tantalizing mysteries. We still do not know the exact depth and extent of the ocean, the distribution of hydrothermal vents, or whether life is present. Cassini proved that Enceladus is habitable, but it could not prove that it is inhabited. That final step awaits future missions. But thanks to Cassini's daring dives, we know where to look, what to measure, and what questions to ask. In the story of exploration, Enceladus's plumes stand as a turning point. They remind us that sometimes the universe offers us shortcuts, cracks in the armor through which secrets spill. Instead of drilling kilometers of ice, we were able to fly through a fountain. Instead of speculating endlessly, we had data in hand. The cosmos, in this case, met us halfway. And as Cassini's instruments recorded the chemistry of another ocean, humanity tasted, for the first time, the breath of a distant sea. When Cassini ended its mission in September 2017 by plunging into Saturn's atmosphere, it left behind a legacy of discovery and a set of urgent questions. Chief among them, does life exist in the ocean beneath Enceladus's ice? Cassini proved habitability. It confirmed water, salts, organics, and hydrogen, all signs that the conditions are right. But it lacked the instruments to make the leap from habitable to inhabited. The next generation of missions must attempt what Cassini could not, to directly search for life. Scientists around the world, energized by Cassini's revelations, have sketched ambitious plans. These concepts range from orbiters circling Enceladus to landers touching its tiger stripes, to spacecraft designed specifically to scoop and analyze the plumes. Each carries its own challenges, costs and promises, but together they form a roadmap for one of the most compelling quests in planetary exploration. The simplest and most immediately feasible mission is the Plume Scooper, a spacecraft that, like Cassini, would fly through the jets of Enceladus, but with instruments designed specifically for life detection. Cassini's mass spectrometers were powerful, but they were built in the 1990s, long before anyone expected to find geysers at Enceladus. They could detect broad categories of molecules, but not the detailed biosignatures astrobiologists now seek. A new mission, armed with advanced spectrometers capable of distinguishing amino acid chirality, lipid structures, or even fragments of nucleic acids, could provide the decisive evidence. The beauty of this concept is its elegance. Enceladus is already delivering samples into space. All a spacecraft needs to do is collect them, analyze them, and report back. No drilling, no landings, just a daring series of high-speed flybys through Saturn's most extraordinary fountain. Proposals along these lines have already been made. The Enceladus Life Finder, ELF mission, championed by planetary scientists in the 2000s, envisioned precisely this approach. ELF would carry next-generation mass spectrometers and dust analyzers, optimized for biomarker detection. Flying repeatedly through the plumes, it would search not only for organics, but for the chemical fingerprints of biology, patterns of isotopes, molecular asymmetry, and specific combinations that point toward life, rather than abiotic chemistry. ELF never moved beyond the proposal stage, but its vision remains central to the future of Enceladus exploration. A step beyond the Plume Scooper is the orbiter. An Enceladus orbiter would remain in constant proximity to the Moon, conducting long-term studies of its plumes, surface, and interior. Unlike Cassini, which could only make occasional flybys, an orbiter could sample the jets repeatedly, track their variability, and map the fissures in detail. It could deploy radar to probe beneath the ice, magnetometers to refine models of the ocean, and high-resolution cameras to reveal the geology of the tiger stripes at scales Cassini could never reach. Over months or years, an orbiter could build a comprehensive picture of Enceladus as a living world. Orbiting Enceladus is not trivial. The Moon is small, and Saturn's gravity dominates the system. Maintaining a stable orbit would require careful navigation and frequent corrections. Radiation, though less intense than around Jupiter, is still a concern. But the payoff would be immense. An Enceladus orbiter would transform our understanding of this moon from snapshots into a continuous story, a moving portrait of a world alive with activity. The most ambitious and the most tantalizing concept is the lander. While flying through plumes offers indirect access to the ocean, a lander would touch the surface itself, planting instruments directly onto the tiger stripes. From there, it could scoop freshly fallen plume material, analyze it in situ, and search for complex molecules or even microscopic life. Cameras could capture close-up images of fissures and icy crystals. Seismometers could listen for the rumble of activity beneath the crust, and drills could penetrate a short distance into the ice. For the first time, humanity would stand, if only with robotic feet, on the surface of a moon that may harbor life. The challenges, however, are formidable. Landing on Enceladus means contending with extremely low gravity, less than 1% of Earth's, making it tricky to anchor and avoid bouncing back into space. The surface around the tiger stripes may be unstable, coated with fine frost or fractured ice. The temperatures plunge to minus 200 degrees Celsius, requiring robust heaters and insulation. Sterilization is also critical. Planetary protection protocols demand that no Earth microbes contaminate Enceladus's pristine environment, especially near the fissures where ocean water is exposed. This means a lander must be built, launched, and sterilized to levels far stricter than Mars rovers, an expensive and technically demanding process. Despite these obstacles, lander concepts have been seriously studied. NASA's Enceladus Orbilander, a hybrid mission proposed in the 2020s, represents one of the most detailed plans yet. It would begin as an orbiter, studying Enceladus from above, then transition into a lander for direct sampling. The Orbilander would carry instruments to detect biosignatures, analyze plume deposits, and even perform in situ microscopy, attempting to spot microbes directly. Though still in the conceptual stage, Orbilander embodies the dream of turning Cassini's discoveries into definitive answers. Beyond landers, visionaries imagine even bolder missions: drills, cryobots, and eventually submersibles, similar to the concepts proposed for Europa. Enceladus, with its thinner ice shell near the South Pole, is actually a more accessible target for such technologies. A nuclear-powered cryobot could melt its way through kilometers of ice, trailing a fiber optic tether, before releasing a hydrobot into the ocean. Such a mission lies decades in the future, requiring advances in power systems, sterilization, and autonomy. Yet the prospect fuels the imagination. The idea of swimming a robotic sub through Enceladus's alien seas, lights cutting through black water, perhaps revealing hydrothermal vents, or even life itself. What unites all these mission concepts, scooper, orbiter, lander, cryobot, is their focus on astrobiology. Enceladus is unique in this regard. Mars exploration is about geology and the search for ancient life. Europa missions balance habitability studies with broad planetary science. But Enceladus presents a direct, urgent question. Is there life in its ocean right now? Its plumes make this a question within reach, one that can be answered with current or near-future technology. Few places in the solar system offer such a straightforward path to such a profound discovery. Each proposed mission also reflects the growing appetite for international collaboration. Just as Cassini was a joint NASA-ESA effort, future Enceladus missions may bring together agencies from Europe, the United States, Japan, and beyond. The costs are high, the risks daunting, but the reward, the discovery of life, would be a prize for all humanity. The scientific, cultural, and philosophical impact would dwarf any investment. It is not only a scientific imperative, but a civilizational milestone. In the meantime, Enceladus remains a silent fountain, its geysers continuing to spray into space as they have for millennia. Cassini proved that those sprays carry the chemistry of life, but the story is unfinished. The next mission, whether a plume scooper, an orbiter, or a lander, will carry our curiosity further. It will attempt to answer the question Cassini raised, but could not resolve. Is Enceladus merely habitable, or is it inhabited? When that mission launches, it will carry with it not just instruments and detectors, but the weight of human longing. For to scoop the plumes, to land on the ice, to pierce the ocean, is to reach across the void and touch another world's most intimate secret. Enceladus, the small moon once ignored, has become one of the grandest stages for human exploration. And the missions now on the drawing board are the first steps toward revealing whether its ocean is silent water or a living sea. In the pantheon of ocean worlds, Enceladus holds a position both improbable and profound. It is tiny, a moon so small that a casual glance through a telescope barely distinguishes it from a star. And yet, thanks to Cassini, we now know that beneath its icy shell lies a vast, salty, dynamic ocean, one that vents into space in magnificent geysers, rich with the chemistry of life. The evidence has accumulated like brushstrokes on a canvas, And though no single detail proves the existence of biology, together they paint a picture so compelling that Enceladus has become one of the strongest contenders for life beyond Earth. To weigh the case for Enceladus as a life world is to examine not only its ingredients, but the philosophy of life itself. The first and most decisive factor is water. Enceladus possesses it in abundance, locked beneath an ice shell but liquid nonetheless. Unlike Mars, where water is patchy, ancient, or buried deep underground, Enceladus has a global ocean in active communication with its surface. The plumes are proof. Ocean water surges upward through fissures, erupting into space. There is no ambiguity here. Of all the requirements for habitability, liquid water is the most fundamental, and Enceladus has it in spades. Next comes chemistry. Cassini revealed that Enceladus's ocean is not pure water, but briny, laced with salts, carbonates, and organics. It is a chemically rich environment, similar in many ways to Earth's oceans. The presence of complex organics, large carbon-based molecules, suggests prebiotic chemistry at work. On Earth, such molecules formed the stepping stones toward life, eventually giving rise to membranes, proteins, and genetic material. Whether Enceladus's organics arise from simple abiotic processes or more complex pathways is uncertain, but the fact that they are present makes its ocean fertile ground for speculation. Then there is energy. Life requires not only ingredients, but a power source to drive metabolism. On Earth, sunlight feeds photosynthesis. But in the depths of our oceans, far from light, hydrothermal vents sustain lush ecosystems powered by chemical energy. Cassini's detection of molecular hydrogen in Enceladus's plumes was therefore one of the mission's most significant discoveries. Hydrogen is produced when hot water interacts with rock in hydrothermal systems. And microbes on Earth thrive on it, using it as fuel. This single detection transforms Enceladus from a passive ocean into an active, energy-rich environment. It is not merely habitable in theory, it is chemically dynamic in ways we know can support life. The case strengthens further when we consider time. Habitability requires not only the right conditions, but also longevity. Life needs time to arise and adapt. Models suggest that Enceladus's ocean may have persisted for billions of years, sustained by tidal heating from Saturn and its orbital resonance with Dione. This longevity means the ocean is not a fleeting phenomenon, but a stable environment where evolutionary processes could take hold. It has had time enough for chemistry to experiment, to stumble toward complexity, perhaps even toward biology. Critics, of course, remind us of the limits of inference. Organics do not equal life. Hydrogen does not equal metabolism. Salts do not equal biology. It is possible, indeed some would argue likely, that Enceladus is sterile, its chemistry intriguing, but lifeless. Abiotic processes can account for many of the observations. Methane, for example, can form through serpentinization without microbes. Complex organics can arise from hydrothermal chemistry without biology. In this view, Enceladus is fascinating but empty, a laboratory of prebiotic processes that never cross the threshold into life. And yet, the parallels to Earth are difficult to dismiss. Everything we know about life's origins suggests that hydrothermal systems, rich in hydrogen and minerals, played a crucial role. If those same processes are occurring on Enceladus, then the leap to life seems less improbable. To assume otherwise is to imagine that Earth is uniquely fortunate, a cosmic anomaly. But if life emerged here in the presence of water, chemistry, energy, and time, why should it not arise there under the same circumstances? This is the heart of the case for Enceladus, that biology is not miraculous but inevitable when conditions align. Beyond the scientific case lies the symbolic weight of Enceladus. It reminds us that the universe is stranger and more generous than we once believed. A moon, no larger than England, orbiting far from the sun, has become a candidate for life. This overturns old paradigms of habitability, which confined our search to Earth-like planets in the Goldilocks zone. Enceladus proves that habitable worlds can exist in darkness, warmed not by sunlight but by gravity, powered not by photosynthesis but by chemistry. It expands the stage of life beyond planets to moons, beyond star-warmed worlds to those lit only by tidal fire. The astrobiological stakes are enormous. If a future mission were to detect life in Enceladus's plumes, even the faintest traces of microbial cells or biomolecules, it would mean that life is a cosmic commonplace. Two origins of life in one solar system would imply billions more across the galaxy. The discovery would reshape not only science but philosophy, religion, and culture. We would know finally that we are not alone. Conversely, if Enceladus proves sterile despite its rich conditions, that too would be profound. It would suggest that life's spark is far rarer than we hoped, that habitability does not guarantee biology, and that Earth may be exceptional in ways we barely comprehend. Either way, Enceladus holds the key to one of humanity's deepest questions. There is also a practical case for prioritizing Enceladus. Unlike Europa, whose thick ice shell makes direct access difficult, Enceladus offers its secrets freely. Its plumes vent ocean material into space, where spacecraft can sample it without drilling. The accessibility of its ocean makes it one of the most cost-effective targets in astrobiology. This efficiency adds weight to the argument. If we truly want to search for life, Enceladus is the low-hanging fruit. Ultimately, the case for Enceladus as a life world is not built on certainty but on convergence. Each piece of evidence, water, salts, organics, hydrogen, heat, longevity, is a brushstroke. Alone, they prove nothing. Together, they form a portrait of a world that seems almost designed for biology. Whether that portrait depicts reality or only potential is the question future missions must answer. For now, Enceladus stands as one of the most compelling places to look for life in the cosmos. A tiny moon with an ocean vast enough to hold secrets that could redefine our place in the universe. Titan, the alien Earth. When Voyager 1 flew past Saturn in November 1980, its cameras turned toward Titan, the planet's largest moon, and saw almost nothing. Instead of craters or mountains, Voyager's images showed a smooth, orange sphere, its features completely obscured. This was unlike any other moon yet encountered. Every other satellite in the solar system revealed itself in some way. Icy grooves on Ganymede, volcanic plumes on Io, jagged cliffs on Miranda. Titan, however, remained hidden, wrapped in a dense haze that refused to let light escape. Scientists were frustrated, but fascinated. A moon with an atmosphere thick enough to conceal its surface was unprecedented. Titan, it seemed, was more than just another frozen satellite. It was a world in its own right. That atmosphere, as subsequent analysis revealed, is rich in nitrogen, making Titan the only moon in the solar system with a nitrogen-dominated atmosphere like Earth's. It is dense, about 1.5 times the pressure at sea level on Earth, and extends hundreds of kilometers into space. Within it, methane and ethane play the role water does on Earth, cycling between liquid and gas, forming clouds, rain, and rivers. For the first time, humanity confronted the idea that another world might possess a climate, a hydrological cycle, not of water but of hydrocarbons. Titan is, in this sense, an Earth in negative, similar in structure but alien in substance. The origins of this atmosphere remain mysterious. For such a small body, only about 40% the diameter of Earth. Retaining a thick atmosphere over billions of years seems improbable. Gravity alone should not suffice. The sun's radiation should have stripped it away. Some scientists suggest that Titan's atmosphere is continuously replenished, with methane outgassing from its interior or from reservoirs beneath the surface. Others argue that photochemical reactions in the upper atmosphere recycle methane, though not fast enough to explain its persistence. Whatever the mechanism, the result is astonishing. A moon wrapped in an atmospheric shroud, thicker and more enduring than Mars, more substantial than Mercury. Titan's atmosphere is not merely thick, it is active. Voyager's instruments detected layers of haze composed of organic molecules formed when sunlight and Saturn's magnetospheric particles strike methane, breaking it apart and recombining it into complex hydrocarbons. These molecules clump together into aerosols, giving Titan its characteristic orange color. Over time, they settle to the surface as a kind of organic rain, coating the moon in a dark, tar-like material. It is as if Titan is constantly manufacturing the raw ingredients of life in its skies and depositing them on the ground in a steady drizzle of prebiotic chemistry. This chemical richness makes Titan unique among moons. Whereas Europa and Enceladus tantalize us with subsurface oceans hidden beneath ice, Titan tempts us with a surface drenched in chemistry, where molecules similar to those that seeded life on Earth are abundant. In this sense, Titan offers a laboratory for studying the pathways from chemistry to biology. It is a world where organic molecules are not rare traces, but the very fabric of the environment, raining from the skies, pooling in lakes, and embedding themselves in soils. Cassini, which arrived at Saturn in 2004, pierced deeper into Titan's mysteries. With radar capable of seeing through the haze, Cassini mapped rivers, lakes and seas of liquid methane and ethane. It watched clouds drift and storms gather, proof that Titan's climate is dynamic. When the Huygens probe, a European lander carried by Cassini, descended through Titan's atmosphere in January 2005, it sent back the first images from the surface. They revealed rounded pebbles of water ice scattered across a floodplain, evidence of liquid erosion. For the first time, humanity stood, virtually, on the surface of a world with rivers and rain, not of water, but of hydrocarbons. The atmosphere was key to this revelation. Without it, Titan would be another frozen moon, cold and inert. With it, Titan is alive with weather. Methane evaporates from seas, forms clouds, and falls as rain. Rivers carve channels, feeding into lakes and seas. Winds sculpt dunes across vast plains. In some regions, seasonal storms may reshape the surface dramatically, much as monsoons do on Earth. Titan's atmosphere, in short, drives a climate system that mirrors our own in structure, while remaining utterly alien in substance. For astrobiology, Titan's atmosphere is a treasure chest. The haze layers are laboratories of photochemistry, producing nitriles, hydrocarbons, and other complex organics. Some of these molecules are similar to those thought to have been precursors to life on the early Earth. In Titan's cold environment, they accumulate rather than decompose, creating a vast archive of prebiotic chemistry frozen in time. Studying Titan is like stepping into a chemical time machine, offering a glimpse of what Earth's atmosphere might have looked like before life arose. Yet Titan is not merely a frozen relic. The interaction between its atmosphere and surface creates possibilities for habitability. Some scientists speculate that beneath its icy crust lies a global water ocean, kept liquid by tidal heating, much like Europa and Enceladus. If true, Titan would be a world with two oceans, one of hydrocarbons at the surface, another of water beneath. The potential for habitability thus doubles, with life as we know it possible in the subsurface, and life, as we do not know it imaginable in the methane seas. Could there be exotic organisms that metabolize methane, using hydrogen instead of oxygen, and ethane instead of water? Titan invites us to stretch the definition of life itself. The atmosphere, with its dense pressure, would even make human exploration easier. Unlike airless worlds, Titan provides natural shielding against radiation, a stable environment where parachutes can work and flying vehicles can glide. Indeed, Titan's thick air and low gravity make it one of the easiest places in the solar system to fly. Future missions like Dragonfly, a nuclear-powered rotorcraft scheduled to launch in the 2030s, Band. Dryage of this, exploring Titan's surface not with wheels but with whirring blades. Without its atmosphere, such a mission would be impossible. From a distance, Titan is a smudged orange orb. Up close, it is a world alive with chemistry, weather, and geology. Its atmosphere is both a veil and a key, concealing the surface while creating the conditions that make Titan extraordinary. It transforms the moon from a dead rock into an alien Earth, a place where rain falls, rivers run, and seas glisten under a pale orange sky. To breathe Titan's air would be impossible. It is nitrogen and methane, unbreathable for humans. Yet to stand beneath its clouds would be to stand on the threshold of another kind of Earth, one that reflects our own in eerie, inverted ways. Titan's atmosphere makes it not only a scientific prize, but a cultural one. It captures our imagination because it feels both familiar and alien, because it hints at a mirror Earth where the roles of water and methane have been exchanged. It forces us to confront the possibility that life need not follow our pattern, that the cosmos may harbor forms of biology so different from our own that we can scarcely imagine them. And it invites us to explore, to send probes, drones, and perhaps one day people, to walk along the shores of methane seas beneath skies dimmed by orange haze. When Cassini first turned its radar toward Titan's North Pole, scientists were stunned by what emerged from the haze. Instead of craters or icy highlands, the images revealed vast, dark patches, smooth, flat regions stretching for hundreds of kilometers. These were not impact basins or frozen plains. They were seas, filled not with water, but with liquid methane and ethane. For the first time in history, we had found standing bodies of liquid on another world. It was as though Earth had been mirrored in distant space, its oceans replaced by hydrocarbons, its clouds and rain composed of chemicals alien to us, but familiar to Titan. The largest of these seas are true inland oceans by terrestrial standards. Kraken Mare, the greatest of them all, covers an area larger than the Caspian Sea and plunges to depths of hundreds of meters, perhaps even a kilometer in places. Ligeia Mare and Punga Mare, smaller but still vast, complete the triad of Titan's northern seas. These bodies are connected by rivers and channels, their shorelines sculpted by erosion and deposition. Cassini's radar revealed river deltas fanning into the seas, their branching patterns eerily similar to those of the Nile or Mississippi. For a moment, it was easy to forget that this was Saturn's moon, and not Earth itself. The existence of these seas solved one of Titan's greatest mysteries. Where does the methane go? Sunlight, weak though it is at Saturn's distance, breaks down methane in Titan's atmosphere over timescales of tens of millions of years. Without replenishment, Titan's methane should have vanished long ago. The seas, lakes, and rivers provide at least part of the answer. They act as reservoirs, storing methane that evaporates into clouds, rains back to the surface, and flows through channels. Titan has a full-fledged hydrological cycle, but with methane standing in for water. Clouds form in the atmosphere, rain falls in storms, rivers carve valleys, and seas lap against shores. It is the same cycle that shapes Earth's landscapes, translated into alien chemistry. The rivers themselves are remarkable. Cassini's radar and infrared instruments traced their winding paths for hundreds of kilometers, cutting through highlands and carving canyons. In 2012, Cassini spotted a river system more than 400 kilometers long, reminiscent of Earth's great rivers. These channels, dark with liquid methane, confirm that Titan's surface is not static, but dynamic, reshaped by climate and flow. The rounded pebbles photographed by Huygens during its descent suggest that erosion and transport are active processes, wearing down icy bedrock just as rivers sculpt rock on Earth. Titan's rivers may one day even rearrange entire landscapes, given time. The seas are not only static reservoirs, they are alive with weather. Cassini observed clouds forming over the poles, and on rare occasions, storms unleashing torrents of methane rain. In one dramatic event in 2010, radar images revealed that vast areas of Titan's surface had darkened, as though drenched by rainfall. The storm had spanned thousands of kilometers, an alien monsoon sweeping across Titan's equator. Such events, though infrequent, demonstrate that Titan's methane cycle is not only theoretical, but active, reshaping the Moon in real time. The physics of these seas is as fascinating as their existence. Titan's low temperatures, about -180 degrees Celsius, keep methane and ethane liquid. Yet the seas are not pure. Cassini detected variations in composition. Ligeia Mare, for instance, is rich in methane, while Krakenmeer contains more ethane and nitrogen. Seasonal changes likely alter the balance as evaporation and rainfall vary. Winds blow across their surfaces, raising waves that Cassini may have glimpsed as magic islands, transient radar reflections thought to be caused by waves, bubbles or floating debris. If confirmed, it would mean Titan not only has seas but also waves, tides, and currents. A true marine system, alien but familiar. The interaction between Titan's seas and atmosphere creates fascinating possibilities. Methane evaporation cools the surface, driving convection and cloud formation. Rainfall alters the chemistry of the lakes. Seasonal cycles tied to Saturn's 29-year orbit may dramatically reshape the distribution of liquids, with seas expanding and contracting over decades. Some models even suggest that the southern hemisphere once held seas like those now in the north, and that Titan's climate shifts liquid from pole to pole over millennia. In this sense, Titan is not static, but evolving, its hydrocarbon climate as dynamic as Earth's. The astrobiological implications are profound. Titan's seas represent a new kind of environment, one never before encountered in nature. Life as we know it depends on liquid water. But could there be life that thrives in liquid methane? Some scientists have speculated that exotic organisms could metabolize hydrogen, acetylene, or ethane, constructing cell membranes not from phospholipids, but from acrylonitrile, a molecule abundant on Titan. These hypothetical azotosms would be stable in methane the way our cells are stable in water. If such life exists, it would be truly alien, a second genesis utterly independent of Earth. Titan's seas, in this sense, are laboratories not just for astrobiology, but for xenobiology, a test of how flexible life can be. Even if Titan proves lifeless, its seas remain invaluable. They preserve a record of organic chemistry stretching back eons, frozen at temperatures where reactions proceed slowly and molecules endure. By studying them, we could learn how prebiotic chemistry evolves, how simple molecules combine, and how complexity arises. Titan may not host life itself, but it may host the chemistry that precedes it, a living archive of what Earth's early atmosphere and oceans might have resembled before biology emerged. Future missions hold the promise of unlocking these mysteries. Dragonfly, the rotorcraft scheduled to launch in the 2030s, will explore Titan's surface, hopping from dune fields to ancient impact craters. Though it will not land in the seas, it may study nearby deposits and weather patterns, offering indirect insights into their composition. Other mission concepts like Titan Mare Explorer, teeming, envision floating probes designed to splash down into Kraken Mare and sail its alien waters. Such a mission could analyze the liquid directly, measure its depth, and even detect waves lapping against its hull. The prospect of a boat on a sea of methane, sending back images of alien shores under an orange sky, captures the imagination as few visions of exploration can. Standing on the edge of Kraken Mare, if one could survive the cold and breathe the atmosphere, would be a surreal experience. The sea would stretch to the horizon, dark and glassy, reflecting the dim light of a distant sun. Above, methane clouds might drift lazily, tinged orange by the haze. Along the shore, waves of liquid hydrocarbons would lap against icy rocks. Not salt water, but methane, clear and alien. It would be a scene at once familiar and unearthly. A reminder that the cosmos echoes Earth in strange, inverted forms. Titan's seas of methane challenge our assumptions about habitability. They remind us that life need not be confined to Earth-like conditions, that planets and moons can host climates and oceans built on entirely different chemistries. They invite us to think more broadly, to imagine not just where life might survive, but how it might innovate. In Titan's seas, the universe shows us a mirror of Earth, not identical, but reversed. An alien Earth where methane takes the role of water, where nitrogen cloaks the skies, and where the dream of other kinds of life lingers just beneath the waves. On January 14th, 2005, humanity achieved something extraordinary. For the first time, a spacecraft landed on a world beyond Mars. The Huygens probe, built by the European Space Agency, and carried to Saturn aboard NASA's Cassini spacecraft, descended through the orange skies of Titan and settled gently on its surface. It was a moment of triumph, a technical feat that blended engineering, vision, and daring. More than that, it was the first and only time we have physically touched Titan, the only probe ever to rest on a moon in the outer solar system. Huygens began its descent more than 1,000 kilometers above Titan's surface, plunging into an atmosphere thicker than Earth's. Its heat shield glowed as it encountered the upper haze, protecting the instruments inside from the friction of entry. Unlike the thin air of Mars, Titan's dense atmosphere allowed for a slow, controlled descent. After the heat shield did its work, parachutes deployed, slowing the probe's fall to a graceful drift. Over the next 2.5 hours, Huygens floated downward, sending back a torrent of data to Cassini, which relayed it across the vast gulf of space to Earth. As it fell, Huygens passed through layers of haze. Orange aerosols of complex hydrocarbons formed high in the atmosphere. Sunlight scattered through the haze, dimming the view, but cameras gradually began to glimpse the landscape below. The first images showed branching networks of dark channels, sinuous and winding, converging like tributaries into broad, dark plains. It was a landscape carved by liquid, eerily reminiscent of aerial photographs of river deltas on Earth. Here was proof that Titan was not a static ball of ice, but a dynamic world, shaped by rainfall and erosion. The descent also revealed clouds drifting in the atmosphere, patches of methane mist hovering near the surface. Instruments detected wind speeds, temperature gradients, and the composition of the air. Nitrogen dominated, just as on Earth, but methane was abundant, along with trace hydrocarbons and complex organics. Titan's atmosphere, Huygens confirmed, was a cauldron of chemistry, rich with the ingredients that might precede life. The haze, layers above, scattered light so thoroughly that the sun was barely more than a glow, a constant twilight under an orange sky. As Huygens neared the surface, its cameras sharpened the view. A floodplain strewn with rounded cobbles, as though a river had once swept through. The rocks were not stone, but water ice, hardened in the cold. Their rounded shape suggested erosion, that they had been tumbled and smoothed by the flow of liquid methane. The plains looked damp, their texture darker in some regions, as though coated by moisture. Indeed, Huygens's instruments hinted that the surface where it landed was soft, yielding slightly under its weight, as if it had touched down on wet sand. The landing itself was gentle. The probe touched Titan's surface at about 4.5 meters per second, bouncing slightly before coming to rest. It continued transmitting for more than an hour after touchdown, the first and only human voice from Titan's surface. Images from the ground showed a flat, pebbled landscape stretching into the haze, dimly lit under the amber sky. The cobbles around the lander were frozen water ice, coated with darker organic material, the residue of Titan's atmospheric chemistry. For the first time, humanity saw what it would look like to stand on Titan. A barren but strangely familiar scene, like a dried riverbed on Earth, painted in alien hues. The data from Huygens confirmed much of what scientists had long suspected. Titan's surface is shaped by liquids, with channels, floodplains, and erosion patterns strongly resembling Earth's hydrology. But instead of water, the fluids are methane and ethane. Titan has rain, rivers, and perhaps occasional floods, carving the icy crust into patterns indistinguishable from those carved by water on Earth. The analogy was so close that geologists studying Huygens's images often compared them to satellite photos of terrestrial river systems. In Titan's alien chemistry, they saw a mirror of Earth's familiar processes. What astonished scientists most was how alive Titan's surface appeared, not biologically alive, but geologically and climatically active. Before Cassini-Huygens, many expected Titan to be ancient and static, its surface unchanged for eons. Instead, Huygens revealed a world sculpted by weather, where erosion continues, where liquids flow, where the surface is replenished. This activity, combined with the dense atmosphere, makes Titan the most Earth-like body in the solar system. No other moon, no other planet, shows such familiar processes at work on such an alien stage. The success of Huygens also demonstrated the value of international collaboration. The probe was built by the European Space Agency, carried by NASA's Cassini, and relayed data back through a network of ground stations around the world. It was a triumph of cooperation, a reminder that exploring the cosmos is not the endeavor of one nation, but of humanity as a whole. Together, agencies and engineers accomplished something no one could have done alone, placing a probe on the surface of a moon more than 1 billion kilometers away. Culturally, the images from Huygens were as powerful as the science. They gave us a visceral sense of Titan as a place. Before Huygens, Titan was a concept, a world of speculation, hidden beneath haze. After Huygens, it was real. It had skies and landscapes, rivers and plains. It was a world where one could imagine standing, walking, even sailing. The photographs, dim and grainy though they were, joined the iconic images of space exploration, Apollo's footprints on the moon, Vikings' vistas of Mars, Voyager's portrait of Earth as a pale blue dot. Huygens gave Titan a face, and with it, a place in the story of exploration. Yet the mission was also bittersweet. Huygens carried no instruments to detect life. Its lifespan was measured in hours, its data limited by design. It provided a tantalizing glimpse, but not the depth of analysis that scientists craved. For all it revealed, Huygens also left us hungry for more. What is the composition of Titan's seas? How do its methane clouds form and dissipate? Does its subsurface ocean harbor life? These questions remain unanswered, waiting for future missions like Dragonfly to pick up where Huygens left off. Still, the descent of Huygens remains one of the great milestones of planetary exploration. It was a moment when humanity extended its reach to the outer solar system and touched, however briefly, a world that mirrors our own in haunting ways. For a few precious hours, a machine built by human hands sat beneath Titan's skies, recording its secrets and sending them across the void. The memory of that day endures, a testament to curiosity, ingenuity, and the unquenchable desire to know what lies beyond. To imagine the scene is to conjure an otherworldly stillness. The lander sits on a frozen floodplain, surrounded by pebbles of ice, beneath a dim orange twilight. Above, methane clouds drift slowly, unseen in the haze. In the distance, rivers carved by alien rains wind their way toward unseen seas. The air is cold, the silence profound. And yet, in that silence, there is also a voice. The voice of data transmitted across the void, telling us that Titan is real, tangible, waiting. Huygens gave us that voice, and in doing so, transformed Titan from myth into reality. If Europa and Enceladus capture our imagination with their hidden oceans, Titan draws us in with something more subtle, but equally profound. Its chemistry. Titan is not merely a moon with lakes and rivers of methane. It is a giant chemical factory, endlessly producing complex organic molecules in its atmosphere and raining them down onto its surface. For scientists interested in the origins of life, Titan is not just a curiosity. It is a natural laboratory, running experiments on prebiotic chemistry across a whole world. The process begins high in Titan's atmosphere. Sunlight, weak though it is at Saturn's distance, carries enough energy to break apart methane molecules. Once freed, the carbon and hydrogen atoms recombine into more complex hydrocarbons: ethane, propane, acetylene. Nitrogen, the dominant component of Titan's atmosphere, is also split by high-energy particles from Saturn's magnetic field. These nitrogen atoms recombine with carbon to form nitriles and other nitrogen-bearing organics. Over time, these reactions build increasingly complex molecules, some with dozens or hundreds of atoms. The atmosphere becomes a soup of chemistry, a haze thick enough to shroud the entire moon in orange. The particles of haze eventually grow large enough to drift downward, settling on Titan's surface like a drizzle of chemical snow. Over billions of years, this organic rain has coated Titan with a layer of dark material. Tholins, as scientists call them. Tholins are not life, but they are rich, tar-like organics that may represent the intermediate steps between chemistry and biology. They form spontaneously under energy input, and on Earth they are thought to have played a role in the prebiotic chemistry that led to the first living cells. Titan, then, offers a world-sized archive of such material, preserved in the deep freeze of its environment. What makes Titan's chemistry especially fascinating is the interaction between these organics and its unique hydrological cycle. Methane and ethane not only rain and pool, but also dissolve and transport tholins, redistributing them across the landscape. River channels seen by Cassini may carry not only liquid methane, but also suspended organic particles, depositing them in deltas and seas. On Earth, rivers and oceans act as mixing bowls for chemistry, concentrating molecules and driving reactions. On Titan, hydrocarbons may play a similar role, creating local environments where organics accumulate, react, and perhaps even edge toward the threshold of biology. The potential for prebiotic chemistry extends below the surface as well. Many scientists suspect that beneath Titan's icy crust lies a global water ocean, kept liquid by tidal heating. If so, then Titan is doubly intriguing. An upper world of methane seas and an inner world of liquid water. Organics raining from the atmosphere could be transported downward through cracks or impacts, mixing with the subsurface ocean. In such a setting, two great ingredients of life, water and organics, would meet. The possibility of life, therefore, exists both at the surface in exotic methane-based forms and beneath the crust in more familiar water-based ecosystems. Astrobiologists are especially intrigued by Titan's potential for alternative biochemistry. On Earth, cell membranes are made of phospholipids, molecules that form stable bilayers in water. In methane, however, these would not work. Instead, researchers have proposed structures called azotosomes, built from nitrogen-rich molecules like acrylonitrile, which Cassini confirmed is present in Titan's atmosphere. In laboratory simulations, azotosomes appear capable of forming stable, flexible membranes in liquid methane. If Titan hosts life, it may be built not on water and lipids, but on methane and azotosomes, a biochemistry wholly alien yet chemically plausible. Such a discovery would revolutionize our understanding of biology, proving that life need not follow Earth's template. Even without life, Titan provides insights into the chemistry that precedes it. By studying its atmosphere and surface, scientists can reconstruct the pathways by which simple molecules become complex. This is invaluable for understanding our own origins. On early Earth, before biology emerged, the atmosphere was likely filled with methane, ammonia, and other simple molecules. Lightning, sunlight, and volcanic energy drove reactions that created organics. Titan today may resemble that ancient stage, frozen in time. By studying it, we glimpse our own planet's distant past, a prelude to life replaying itself on a grander stage. Cassini's instruments offered tantalizing glimpses of this chemistry. The ion and neutral mass spectrometer detected heavy molecules in Titan's upper atmosphere, some with masses over 1,000 atomic units. Polymers and complex hydrocarbons of a scale approaching biological macromolecules. The haze layers are, in effect, a global organic laboratory, endlessly synthesizing new compounds. On the surface, radar and infrared sensors identified deposits of organics in dunes that stretch for thousands of kilometers, covering equatorial regions in a sea of dark material. These dunes are not sand as we know it, but grains of tholins, sculpted by wind into vast deserts of organic dust. The sheer abundance of organics on Titan sets it apart from any other moon. On Europa or Enceladus, we search for organics as precious traces, possible indicators of habitability. On Titan, organics are everywhere. In the air, on the ground, dissolved in lakes, drifting in haze. If we are looking for chemistry that could evolve toward life, Titan provides it in overwhelming abundance. The question is not whether organics exist, but what processes they undergo in Titan's unique environment. Some scientists have speculated that Titan's surface seas might even host chemical reactions approaching metabolism. In 2010, researchers proposed that hydrogen and acetylene levels on Titan's surface could hint at chemical consumption, possibly by exotic organisms. While such claims remain speculative, they highlight Titan's allure. It is one of the few worlds where entirely new forms of life could plausibly exist. Even the possibility forces us to broaden our imagination, to conceive of life not as a single pattern, but as a spectrum of possibilities. The philosophical impact of Titan's chemistry is immense. It reminds us that the ingredients of life are not rare or confined to Earth. They are written into the physics of carbon, hydrogen, nitrogen, and energy. Given the right conditions, these atoms build complexity spontaneously. Titan demonstrates this on a planetary scale. It is not a world of sterile ice or barren rock, but a world where chemistry dances endlessly toward greater intricacy. Whether the dance has crossed the threshold into biology, we do not yet know. But the stage is set, the actors assembled, the energy supplied. Titan may be right now a world paused at the edge of life. Future missions will probe deeper. Dragonfly, the rotorcraft scheduled for launch in the 2030s, will carry advanced instruments to analyze Titan's organics directly. By hopping across diverse terrains, dunes, craters, plains, it will sample different deposits of tholins and search for patterns in their complexity. If certain regions show chemical organization suggestive of prebiotic processes, it will be the closest we have come to watching the dawn of biology in real time. In the long view, Titan may become not only an astrobiological target, but also a proving ground for understanding how life begins everywhere, from exoplanets to icy moons. Titan's alien chemistry, then, is not just a curiosity of planetary science. It is a cosmic story about the universality of carbon, the creativity of chemistry, and the possibility that life is not unique to Earth. By studying Titan, we study ourselves, not our biology as it is now, but our biology as it once was, and as it might be elsewhere. Titan is a reminder that the cosmos is not silent, but endlessly creative, shaping worlds where rivers flow, atmospheres churn, and chemistry builds the scaffolding of life, whether or not biology follows. For decades after Voyager revealed Titan's orange haze, the dream of exploring its surface lingered in the imagination of planetary scientists. Huygens's brief touchdown in 2005 gave us a tantalizing glimpse, but it lasted only hours. Titan is too rich, too complex, too Earth-like, and alien all at once to be understood by a single snapshot. It demands long-term exploration, movement across landscapes, and the ability to sample widely. For years, engineers toyed with ideas. Balloons drifting through Titan's skies, boats sailing its methane seas, landers drilling into icy plains. Then came a bold concept that captured the best of all worlds. A flying laboratory, a nuclear-powered rotorcraft capable of leaping across Titan's surface. Its name, Dragonfly. Dragonfly is unlike any planetary mission ever attempted. Where Mars rovers crawl slowly over rocky ground, Dragonfly will fly. Titan's environment makes this possible in ways unimaginable elsewhere. Its atmosphere is thick, denser than Earth's, and its gravity is weak, about 1/7 of ours. These conditions combine to make flight extraordinarily efficient. A small rotorcraft can lift heavy payloads and travel kilometers at a time with ease. It is, ironically, far easier to fly on Titan than on Earth or Mars. What would be a near impossible challenge in thin Martian air becomes almost effortless beneath Titan's orange skies. Dragonfly's design capitalizes on this. Roughly the size of a small car, with 8 rotors arranged like a scaled-up drone, the craft will carry a full suite of scientific instruments powered by a radioisotope. Thermoelectric generator, RTG. Solar panels would be useless on Titan. The sunlight is too weak, dimmed further by haze. Nuclear power ensures that Dragonfly can operate for years, charging its batteries by day and flying in short hops from one site to the next. Each flight will cover several kilometers, making Titan the first world where humanity explores, not with wheels, but with wings. The mission's goals are as ambitious as its design. Dragonfly will explore diverse terrains, hopping between dunes, craters, and plains, sampling Titan's chemistry along the way. One of its prime targets is Clarke Crater, an ancient impact site thought to have melted Titan's icy crust, creating a transient water environment where organics from the atmosphere could have mixed with liquid water. Such craters may have been crucibles for prebiotic chemistry, much as impact sites on early Earth may have seeded the conditions for life. By studying Selk and its surroundings, Dragonfly will search for signs of complex chemical processes and perhaps the building blocks of life itself. Dragonfly's scientific payload is designed to probe Titan's mysteries in detail. Mass spectrometers will analyze surface samples, detecting organics and searching for patterns that hint at prebiotic chemistry. Cameras and sensors will map the landscape, providing the first high-resolution views of Titan's surface across multiple locations. Meteorological instruments will measure winds, temperatures, and methane humidity, tracking Titan's active climate. A seismometer will listen for quakes, probing the thickness of the ice crust and the possibility of a subsurface ocean. Every instrument is chosen to address the great questions of Titan. What is its chemistry? How active is its geology? Does it host conditions for life? The mission timeline reflects both ambition and patience. Scheduled for launch in the mid-2030s, Dragonfly will take nearly a decade to reach Saturn's system, arriving in the mid-2040s. Once it lands, it will operate in a series of flights, each covering up to 10 kilometers, with rests in between to recharge and analyze samples. Over the course of its mission, Dragonfly is expected to travel more than 150 kilometers across Titan's surface, far more ground than any Mars rover has covered. It will be, in effect, a planetary expedition, leaping from site to site, like an explorer sampling every ecosystem along a continent. What sets Dragonfly apart is its adaptability. Rovers are confined to one terrain, limited by obstacles. Orbiters see everything from above but touch nothing. Dragonfly will bridge the two, able to observe landscapes from the air, land where it chooses, and move on when done. If one site proves uninteresting, it can simply fly to another. If a storm approaches, it can ride it out in safety, then resume exploration. Titan's forgiving environment makes this possible, offering a stage where human ingenuity can play freely. The symbolism of Dragonfly is powerful as well. It represents a shift in planetary exploration toward bold, innovative designs. It reflects a willingness to take risks, to move beyond the safe templates of orbiters and rovers. It also embodies humanity's fascination with Titan, our recognition that this strange moon may hold answers, not only about life beyond Earth, but about life's very beginnings. Dragonfly is not just a mission, it is a declaration that Titan matters, that it deserves the same sustained attention once reserved for Mars. The potential discoveries are staggering. Dragonfly could confirm the presence of exotic organics, even molecules resembling amino acids or lipids. It could reveal patterns in Titan's chemistry that suggest pathways toward biology. It could detect seismic evidence of a subsurface ocean, reinforcing the idea that Titan, like Europa and Enceladus, is a double ocean world. And though the mission is not designed to detect life outright, it could lay the strongest foundation yet for that possibility, showing that Titan is not merely habitable in theory, but chemically active in ways suggestive of biology. Imagine the scenes it may send back. Panoramic images of dune seas stretching for hundreds of kilometers, carved not of sand, but of organic grains. The cratered highlands of Selk, where impacts once mixed water and organics in violent chemistry. The dim glow of the sun filtering through haze, lighting a landscape at once barren and hauntingly familiar. Dragonfly's cameras will show us Titan not as an abstract concept, but as a place, a world with horizons, weather, and texture. We will see, for the first time, the reality of standing beneath its skies. The mission also carries philosophical weight. By exploring Titan, Dragonfly will test the boundaries of our definition of life. If Titan hosts exotic biochemistry, methane-based organisms with structures unlike anything on Earth, it would prove that biology is not a singular template, but a spectrum of possibilities. It would tell us that life adapts to environments in ways more diverse than we dared imagine. Even if no life is found, the mission will show us how far chemistry can progress on its own, revealing whether Titan sits on the threshold of biology or firmly within prebiotic realms. Dragonfly also inspires in another way. It is a human creation designed to fly on alien skies. Just as the Wright brothers opened the age of flight on Earth, Dragonfly will open the age of flight on another world. Its rotors will spin in methane-rich air, lifting it across landscapes billions of kilometers from home. Each hop will be a triumph of imagination, a reminder that the desire to explore knows no bounds. In the end, Dragonfly embodies the essence of exploration: boldness, curiosity, and the pursuit of questions that reach to the heart of who we are. It will carry with it the legacy of Huygens, the discoveries of Cassini, and the dreams of generations who looked at Titan's orange haze and wondered what lay beneath. When it launches, it will not just be a spacecraft heading to Saturn's largest moon. It will be humanity's Dragonfly, hovering between worlds, touching the edge of the possible, and seeking answers in the twilight skies of a methane Earth. When we look at Titan, what captivates us most is not just its strangeness, but its familiarity. It is the paradox of a world that is both profoundly alien and hauntingly Earth-like. Nowhere else in the solar system do we see landscapes so reminiscent of home. Rivers branching into deltas, seas lapping against shores, dunes stretching across plains. Yet every detail is inverted, every similarity clothed in difference. Titan is Earth's mirror, a reflection that shows us what a habitable world can be, but in a form utterly unlike our own. The parallels begin with landscapes. From orbit, Cassini's radar painted Titan in strokes that could easily be mistaken for Earth. Rivers snake across the surface, flowing into broad lakes and inland seas. Their deltas spread like fans, sculpted by erosion and deposition. Vast dune fields cover Titan's equatorial regions, shaped by winds into ridges hundreds of kilometers long. Impact craters pockmark the highlands, their rims softened by erosion. To a geologist, the patterns are instantly familiar. Titan, like Earth, is a world where climate and surface interact, where weather sculpts land into rivers, lakes, and plains. No other moon in the solar system shows such a balance of processes, such an active dialogue between sky and ground. Yet the contrasts are as profound as the parallels. Titan's rivers do not flow with water, but with methane and ethane, hydrocarbons that would be gases on Earth, but are liquid in Titan's cryogenic cold. Its dunes are not made of quartz grains, but of dark organics, tholins, formed in the atmosphere and blown across the surface like alien sand. Its seas are not salty brines, but lakes of liquid methane, glistening under orange haze. Even its bedrock is not rock at all, but frozen water ice, as hard as granite in the minus 180 degrees Celsius cold. Every familiar feature is transformed, every echo of Earth turned inside out. Titan is Earth in chemical negative. Same shapes, same patterns, but built of different stuff. This inversion extends to Titan's climate. On Earth, the hydrological cycle is driven by water. The sun warms the oceans. Water evaporates, clouds form, and rain falls, feeding rivers and seas. On Titan, the same cycle exists. But methane is the working fluid. It evaporates from seas, forms clouds, rains onto the surface, and carves channels. Titan even has storms, monsoon-like downpours that reshape the landscape. The mechanics are the same, the substance wholly different. Titan demonstrates that climate is not unique to Earth, but a universal process that arises whenever a liquid, a gas, and energy interact. It is climate translated into a different chemical language. The atmosphere reinforces this mirror image. Like Earth, Titan's air is dominated by nitrogen, making it the only other world in the solar system with a nitrogen-rich atmosphere. But where Earth's nitrogen is tempered by oxygen, Titan's is filled with methane and smothered in haze. Its skies are orange, its sunlight dimmed to a twilight glow. Standing on Titan would be like standing on Earth beneath perpetual smog, the sun, a pale disk filtered through photochemical fog. Yet despite its gloom, Titan's atmosphere is protective, shielding its surface from radiation and supporting winds, weather, and rain. It creates a world not barren like the Moon, nor exposed like Mars, but alive with processes. The most profound parallels and contrasts lie in habitability. Earth is a biosphere, teeming with water-based life that depends on oxygen, carbon dioxide, and sunlight. Titan, by contrast, may host exotic possibilities. Its subsurface ocean, hidden beneath kilometers of ice, could resemble Europa's or Enceladus's, a water world warmed by tidal heating. There, life as we know it, water-based, carbon-fed, energy-driven, might exist. But Titan's surface offers an even more radical idea: life as we do not know it. Could methane seas host organisms that metabolize hydrogen, exhale ethane, and build cell membranes from acrylonitrile rather than lipids? Such chemistry is alien to us, but not chemically impossible. Titan is a test case for biology beyond the terrestrial template, a place where life may have found a path entirely different from our own. For astrobiology, Titan is invaluable because it stretches our imagination. Europa and Enceladus tempt us with Earth-like analogies: water oceans, hydrothermal vents, familiar pathways to life. Titan challenges us to think differently. It asks whether life can thrive in solvents other than water, whether metabolism can proceed in methane, whether cell membranes can form in liquid hydrocarbons. If Titan hosts life, it would be the most revolutionary discovery imaginable. Proof that biology is not one story but many, that the universe invents life in diverse forms. If it does not, it still shows us how chemistry builds complexity, how prebiotic molecules accumulate, and how the stage can be set for biology even if the play never begins. Titan also offers a mirror for Earth's history. 4 billion years ago, before life arose, Earth's atmosphere may have resembled Titan's, methane-rich, hazy, filled with organic chemistry. Studying Titan is like peering backward in time, watching the chemistry that may have seeded our own origins. On Titan, those processes are frozen, slowed by the cold, preserved as a natural experiment in prebiotic chemistry. Titan may never have crossed the threshold into life, but in studying it, we see the steps that lead toward that threshold. It is a reminder that our own story is not singular, but part of a larger pattern the cosmos repeats in many variations. The human connection to Titan is equally compelling. Unlike most icy moons, Titan is a world we can imagine visiting. Its thick atmosphere shields against radiation. Its gravity is gentle but sufficient. With the right suit, a human could walk on Titan's plains without a pressurized habitat, protected by the dense air. In Titan's low gravity and thick atmosphere, one could strap on wings and fly. It is one of the few worlds in the solar system where human exploration is not only possible, but oddly inviting. That combination of safety and strangeness gives Titan a unique allure. It is both alien and oddly hospitable, a place where we could, in some distant future, stand beneath alien skies and feel a kinship to Earth. The symbolism of Titan as a mirror of Earth resonates deeply. It tells us that our planet is not unique in its processes. Rivers and rain are not exclusive to Earth. They are natural consequences of planetary systems. Climate, geology, and chemistry repeat themselves in different keys across the cosmos. Titan is proof that the universe creates echoes of Earth, worlds where familiar processes unfold in alien ways. It is both a reflection of our planet and a reminder of the diversity of worlds. In the end, Titan's greatest gift is perspective. It shows us that habitability is broader than we thought, that chemistry is more creative than we imagined, and that Earth's story is part of a larger cosmic tale. Whether Titan harbors life or not, it forces us to expand our vision of what life could be. It is Earth's mirror, yes, but not a perfect one. It is distorted, alien, inverted, and in that distortion lies its power. By studying Titan, we study ourselves, our origins, and our place in a universe where Earth may be just one of many kinds of living worlds. Io, hell in the heavens. Among the moons of the solar system, none inspires awe and fear quite like Io. While Europa hides an ocean beneath a frozen shell and Titan dreams of alien chemistry under an orange sky, Io is a world of fire. It is the most volcanically active body known. Its surface a restless canvas of lava flows, erupting plumes and mountains higher than Everest. To look at Io is to glimpse a world caught forever in torment, its interior stretched and squeezed until the very crust cracks open, venting molten rock into space. It is a vision of planetary hell. And yet, like all extremes in nature, it tells us something profound about the workings of the cosmos. At first glance, Io's activity is puzzling. It is a relatively small moon, only slightly larger than Earth's moon. By all logic, such a body should be geologically dead, its primordial heat long since radiated into space. The moon bears silent witness to this fate. Its lava plains solidified billions of years ago, leaving a world of craters frozen in time. Mars, too, larger than Io, has cooled and stilled, its volcanoes extinct for ages. Why then is Io a cauldron of perpetual fire? The answer lies not in its size, but in its position. Caught in the gravitational grip of Jupiter, the largest planet in the solar system, and locked in a resonant dance with its sibling moons. Io orbits Jupiter in just 1.8 Earth days, racing around its planet with dizzying speed. It is locked in a 4:2:1 resonance with Europa and Ganymede, meaning that for every 4 orbits Io completes, Europa completes 2, and Ganymede 1. This resonance keeps Io's orbit slightly elliptical rather than perfectly circular. As Io moves closer to Jupiter, the giant planet's gravity stretches it, raising immense tides, not of water, but of rock. As Io moves farther away, the tension eases. This constant stretching and relaxing kneads Io's interior like dough, generating friction and heat on a colossal scale. The result is tidal heating so intense that Io's mantle churns with magma, its crust riddled with fissures, its surface perpetually broken and renewed. The scale of this energy is staggering. Io emits about 100 times more heat than Earth does per unit of surface area, despite being only a fraction of its size. This heat powers eruptions unlike anything on Earth. Fountains of lava that can hurl molten rock hundreds of kilometers across the surface. Plumes of sulfur and dust that reach higher than Mount Everest into space. And lava lakes so vast, they dwarf terrestrial analogues. Some eruptions on Io have been visible even to telescopes on Earth, glowing beacons of fire across the gulf of space. The eruptions are varied in style and ferocity. Some resemble familiar volcanoes, with lava flowing steadily across plains. Others are explosive, driven by volatile gases like sulfur dioxide that burst from fissures in violent plumes. Still others are persistent features, like Loki Patera, a massive, continuously overturning lava lake larger than Lake Ontario. Io's volcanoes are not occasional spectacles. They are constants. At any given time, dozens of eruptions may be underway, reshaping the surface in a geological instant. The chemistry of Io's eruptions adds to its strangeness. Whereas Earth's volcanoes are dominated by silicate rock, Io's are infused with sulfur and sulfur dioxide. These compounds give Io its surreal, painted surface, with colors ranging from bright yellow to deep red and black. Sulfur frost coats the ground in patches, while lava flows scorch it into darkness. The result is a world that looks as though it has been dipped in fire and ash, a place where geology paints in colors no artist would dare invent. Perhaps the most haunting aspect of Io's volcanic activity is its relentlessness. Unlike Earth, where volcanic eruptions are localized and episodic, Io is a world where eruption is the rule, not the exception. Its surface is in constant flux, a living demonstration of planetary energy unleashed. To walk upon Io, if such a thing were possible, would be to tread a land where the ground itself is never safe, where vents open without warning, where lava rivers can stretch for hundreds of kilometers, and where plumes of sulfur snow rain down from the skies. The spectacle of Io challenges our understanding of what a moon can be. We tend to think of moons as passive companions, shaped by the gravity of their planets, but not dynamic in their own right. Io shatters this assumption. It is not a frozen rock, but a world more active than Earth itself, a planet in miniature, whose energy comes not from radioactive decay or primordial heat, but from the gravitational embrace of its parent planet. It is a reminder that worlds are shaped not only by their birth, but by their relationships, by the constant push and pull of gravity, resonance, and orbital mechanics. Io's eruptions also highlight the extremes of planetary volcanism. On Earth, the largest eruptions in history, the supervolcanoes of Yellowstone or Toba, left scars that lasted for hundreds of thousands of years. On Io, such eruptions are commonplace. Entire regions can be resurfaced in years or decades, erasing craters and leaving a skin of molten rock. Eruptions have been observed where lava flows spread over areas larger than entire countries. If Earth is a geologically restless planet, Io is geologically frantic, a world without pause, where the very concept of geological time collapses into immediacy. The tidal inferno that drives Io also influences its neighbors. The same resonance that keeps Io's orbit eccentric ensures that Europa and Ganymede experience tidal flexing too, though to a lesser degree. In Europa, that energy manifests as cracks and possible subsurface oceans. In Ganymede, it may sustain an internal ocean beneath the ice. Io, Europa, and Ganymede are therefore linked in a chain of gravitational energy, each influencing the other, each bearing the scars of Jupiter's dominance. Io, as the innermost and most tortured, bears the brunt of that energy, turning its entire surface into a volcanic wasteland. To study Io is to study the limits of planetary energy. It is the most extreme example we know of what tidal heating can do, a natural laboratory for processes that may be common in other star systems. Astronomers have already detected exoplanets and exomoons whose orbits suggest they too may be tidally heated. If so, Io offers a glimpse of what those worlds may be like. Volcanic infernos glowing in the dark, their surfaces perpetually remade by fire. There is, of course, beauty in Io's violence. From space, its plumes rise like fountains of light, arcing gracefully before falling back as snow of sulfur. Its surface is a tapestry of colors, painted by chemistry into yellows, oranges, and reds. Its volcanoes are not only destructive, but creative, endlessly renewing the world. Io is hell, yes, but it is also a place of extraordinary vitality, a moon where fire never dies. In the grand story of the solar system, Io reminds us that worlds are not static, but alive in ways we may not expect. Some harbor oceans beneath ice, others breathe chemistry in thick atmospheres. Io burns, It's a world of extremes, a testament to the power of gravity, and a lesson in how planetary energy can shape not only landscapes, but entire worlds. To stand above it, looking down from orbit, would be to see a hell that is also a wonder, a volcanic inferno blazing in the heavens, both terrifying and sublime. When Voyager 1 and 2 swept past Jupiter in 1979, they left humanity stunned. For the first time, volcanic plumes were seen bursting from a world other than Earth. Cameras aboard Voyager captured a plume erupting hundreds of kilometers above Io's surface, a sight so unexpected that at first, scientists doubted their eyes. Until then, no one had ever imagined that a moon could be so violently alive. Voyager's fleeting glimpses transformed Io from a speck of light into the most active volcanic body in the solar system. Yet it was the Galileo spacecraft, arriving in the 1990s, that revealed Io's volcanic world in all its spectacular detail. Galileo, launched in 1989 and arriving at Jupiter in 1995, carried with it the instruments to observe Io repeatedly, over years, not just hours. Where Voyager had shown us sudden eruptions, Galileo painted the broader canvas of activity. Persistent lava lakes, recurring outbursts, plumes so enormous they could wrap Io in transient atmospheres of sulfur. Galileo was a witness to a world in constant renewal. A moon, where fire was not an occasional punctuation, but the ongoing rhythm of its existence. The centerpiece of Galileo's discoveries was Loki Patera, the largest active lava lake in the solar system. Stretching over 200 kilometers across, Loki is more than twice the size of Lake Ontario. Seen in infrared, it glows with shifting patterns of heat as massive overturning events sweep across its surface. Unlike Earth's smaller lava lakes, Loki is a planetary-scale cauldron. Galileo watched as its crust solidified, then sank in great waves, exposing fresh molten lava beneath. This overturning repeats in cycles lasting hundreds of days, creating a volcanic heartbeat that pulses across Io. Scientists describe it as a lava lake on a conveyor belt, its surface constantly renewing, its scale unmatched anywhere else in the solar system. Loki was not alone. Galileo revealed dozens of other active centers, each with its own style and character. Some, like Pele, erupted in dramatic plumes hundreds of kilometers high, powered by sulfur dioxide gas, escaping with explosive force. Pele's plume was so enormous that it created a circular deposit of bright red sulfur compounds over 1,200 kilometers across, painting Io's surface like a cosmic bullseye. Others were more subdued, oozing lava in flows that extended for hundreds of kilometers, reshaping Io's plains in fiery rivers. Some volcanoes erupted with such violence that they expelled material at velocities high enough to escape Io's weak gravity, seeding Jupiter's magnetosphere with sulfur and oxygen. The plumes themselves are unlike anything on Earth. On our planet, volcanic plumes are usually measured in kilometers. On Io, they soar into space. Galileo recorded plumes rising 300 to 500 kilometers above the surface, arching gracefully before collapsing back as sulfur snow. These plumes are not only spectacular but also central to Io's identity. They coat the moon with bright frosts of sulfur dioxide, create transient atmospheres, and feed the Io plasma torus, a giant ring of ionized gas encircling Jupiter. Io's eruptions, in other words, are not confined to its surface. They reshape the entire Jovian system. One of Galileo's most dramatic observations came in 1997, when it captured a colossal eruption at Pilon Patera. Lava fountains exploded from a fissure, pouring molten rock across 4,000 square kilometers, an area the size of Rhode Island. Within months, the eruption buried older terrain, creating new plains of basalt and sulfur compounds. Pilon's eruption was hotter than anything observed on Earth in recorded history, with lava temperatures exceeding 1,600 degrees Celsius, hotter than even Earth's most primitive ancient lavas. Io's interior seemed to channel the heat of creation itself, forging eruptions that rivaled the conditions of Earth's earliest volcanic epochs. Galileo's revelations extended beyond the sheer scale of eruptions. They also showed Io's diversity. Some volcanic centers, like Prometheus, erupted persistently, producing steady lava fountains and plumes for decades. Others flared explosively and then fell silent. Some featured calderas, massive volcanic depressions dozens of kilometers wide, filled with lakes of lava or sulfur. Io was not just active, it was versatile, demonstrating nearly every style of volcanism known on Earth, and some that were entirely alien. What struck scientists most was the tempo. On Earth, even in volcanically active regions like Hawaii or Iceland, eruptions are measured in years or decades. On Io, Galileo witnessed multiple large-scale eruptions during its mission, some reshaping hundreds of kilometers of terrain in mere months. The Moon's surface was not a static record, but a living performance, changing faster than any planetary surface we had ever observed. To study Io was to watch geology in fast forward, a world remade before our eyes. The diversity of volcanic materials added to the strangeness. Sulfur compounds dominated, producing colors that ranged from dazzling yellows to blood reds and deep blacks. Sulfur dioxide frosts gleamed white under sunlight. Basaltic lava, hotter than Earth's, glowed in infrared. Together, these materials created a patchwork surface more vibrant than any other moon, a kaleidoscope of chemical artistry. From orbit, Io resembled a tortured canvas splattered with alien paints, each eruption rewriting the landscape in new hues. Galileo also deepened our understanding of Io's role in the Jovian system. Its constant eruptions supplied material not only to its surface, but to space itself. The gases vented into its thin atmosphere were quickly stripped away by Jupiter's magnetic field, forming the Io plasma torus, a gigantic donut of ionized sulfur and oxygen that encircles the planet. This plasma interacts with Jupiter's magnetosphere, generating auroras at the giant planet's poles, and linking Io's fate to the larger Jovian environment. Galileo confirmed that Io is not an isolated world, but a central player in the electrical and magnetic theater of Jupiter's system. The revelations of Galileo changed the way we think about moons. Before Voyager and Galileo, moons were assumed to be dead worlds, frozen relics of planetary formation. I shattered that assumption. It proved that moons could be as dynamic as planets, their energy drawn not from size but from gravitational interactions. Galileo's close observations turned Io into a case study of tidal heating, a world where orbital resonance and planetary gravity combined to unleash unimaginable fire. For planetary scientists, Galileo's legacy was both thrilling and frustrating. Thrilling because it revealed a world of astonishing dynamism, a volcanic wonderland unparalleled in the solar system. Frustrating because Io remains so hostile that no lander has ever been attempted, and no spacecraft has flown dedicated missions there since. Galileo gave us glimpses, spectacular, detailed glimpses, but not the full story. Many of Io's volcanoes are still mysteries, their cycles poorly understood, their chemistry only partially sampled. The question of a global magma ocean, hinted at by Galileo's magnetometer, remains unresolved. And yet, even in its incompleteness, Galileo's vision of Io is unforgettable. It showed us a world where fire reigns, where volcanoes dominate the landscape, where eruptions are not disasters, but the ordinary rhythm of existence. In Loki Patera's overturning waves, in Pele's towering plume, in Pilon's fiery outburst, We saw not chaos but order, the inevitable outcome of gravity, resonance, and geology. Io is hell, yes, but it is a hell with rules, a system whose beauty lies in its relentless consistency. From Galileo's perspective, Io was never still. It was always glowing, always venting, always changing. It was a reminder that the solar system is not frozen, but alive, dynamic, and surprising. In the 1990s, as Galileo orbited Jupiter, humanity was given a seat at the edge of this inferno, watching a moon that defied every expectation of what a satellite should be. Io, the volcanic world, was revealed in all its terrifying glory, and the vision still burns in our collective imagination. When we look at the moon, or at Mercury, or at many icy moons in the outer solar system, their surfaces bear the scars of cosmic history. Craters, carved by impacts over billions of years, tell stories of bombardment and silence, of planets and moons frozen in time. These impact scars are like wrinkles on an ancient face, indelible, enduring, unmoving. Io, however, tells a different story. It is a world almost entirely without craters, not because impacts never struck it, but because its surface is constantly erased. Volcanism repaves Io so quickly and so relentlessly that no crater, no matter how ancient, survives for long. Io's surface is the youngest in the solar system, a world caught in perpetual renewal. At first, this absence of craters baffled scientists. When Voyager 1 flew past Jupiter in 1979, its cameras captured Io's surface in detail. What they saw was unlike anything expected. Instead of a heavily cratered landscape like Europa or Callisto, Io's face was bizarrely smooth, decorated instead with strange pits, lava flows, and colorful deposits. It was clear that impacts must have occurred. Every body in the solar system is struck eventually, but none had been preserved. The only explanation was that Io's surface was being resurfaced faster than craters could accumulate. Subsequent missions confirmed that this is indeed the case. Eruptions on Io cover vast areas in months or years. Lava floods extend for hundreds of kilometers, blanketing plains and filling basins. Plumes erupt, coating regions with fresh frost of sulfur dioxide. Lakes of molten lava overturn, spreading new crust across calderas. On geological timescales, this activity is instantaneous, a crater that might endure for billions of years. On the Moon, vanishes on Io in a few million, perhaps even in a few 100,000. It is a surface without memory, rewritten again and again in fire. This lack of craters makes Io unique. Where other moons tell us about the early history of the solar system through preserved impacts, Io tells us about the present, about processes still happening now. Its surface is not a fossil, but a performance, one that unfolds continuously before our eyes. In this sense, Io is more like Earth, whose tectonics and volcanism erase craters over time. But while Earth takes millions of years to recycle its surface through plate tectonics, Io does it directly, through volcanism alone, and at a pace Earth cannot match. The results are landscapes both alien and strangely beautiful. Lava flows snake across plains, cooling into black rock that gleams in infrared. Frosts of sulfur dioxide coat regions in bright white, only to be buried by new eruptions. Depressions tens of kilometers wide mark volcanic calderas, some filled with glowing magma, others coated with sulfur compounds. Mountains, taller than the Himalayas, rise where the crust has buckled under stress, their slopes stained by volcanic debris. Everywhere the colors are vivid. Yellows, reds, oranges, blacks, the palette of sulfur in its many forms. Io looks less like a moon and more like a canvas splashed with fire and ash, One of the most telling indicators of Io's resurfacing is its distribution of terrain. Instead of craters, the surface is dominated by volcanic depressions, called paterae. These are not simple impact scars, but collapsed volcanic features, evidence of magma chambers that have emptied and sunk. Over 400 active volcanoes are known, more than any other planetary body. Each eruption adds new layers to the crust, piling one on top of another until older features are buried. Unlike the Moon, where the surface preserves a record of impacts billions of years old, Io's surface is at most a few million years old, and often far younger. Galileo's infrared observations made this constant resurfacing vivid. Time after time it detected new hotspots of activity, regions that glowed with heat where none had before. Within weeks or months, terrain would change. Lava would flow into plains, plumes would blanket surfaces, and entire landscapes would look different from previous flybys. For geologists, it was as if the surface of a planet were alive, shifting visibly in real time. Io was not a frozen relic of the past, but a demonstration of the present, a world defined by change. The absence of craters also underscores the sheer scale of Io's volcanism. On Earth, volcanic eruptions are spectacular but localized. Even our most violent outbursts, such as the eruption of Tambora in 1815, or the flows of Iceland's Laki fissure, affect regions but leave the broader world intact. On Io, eruptions are so vast and so frequent that they transform the Moon globally. Every square kilometer of Io has likely been resurfaced many times since its formation. It is a world that cannot stand still, its skin eternally consumed and reborn. This endless resurfacing has broader consequences. It means that Io's crust is layered in ways unlike any other moon. Instead of ancient rock preserving the memory of formation, its crust is a palimpsest, a stack of lava flows and sulfur deposits of varying ages. It also means that Io may be shedding material into space continuously, not just through eruptions, but through erosion of its volatile frosts. The constant renewal keeps Io geologically young, but it also ties it to Jupiter's magnetosphere, where its volcanic gases become part of a vast electrical circuit around the planet. Io's resurfacing also makes it challenging to study. Unlike the Moon or Mars, where craters provide a reliable clock for dating surfaces, Io defies easy chronology. We cannot simply count craters to estimate ages. Instead, scientists must rely on thermal measurements, plume monitoring, and geological modeling to reconstruct its history. In many ways, Io is more difficult to interpret than more static worlds, because it refuses to hold still long enough for us to take a snapshot of its past. And yet, this very quality makes Io invaluable. By erasing its craters, Io forces us to confront geology as a process, not just a record. It demonstrates what happens when volcanism dominates utterly, when resurfacing is not occasional, but perpetual. It provides a living example of what Earth may have looked like in its fiery youth, before plate tectonics, when magma oceans churned and impacts were quickly erased by flows of molten rock. Io is, in a sense, a time machine, not to the ancient solar system preserved in craters, but to the fiery chaos of planetary adolescence. From orbit, the lack of craters gives Io a strangely smooth appearance, punctuated not by scars, but by features of fire. To look at it is to realize that violence does not always leave wounds. Sometimes it heals them too quickly to see. Io's face is forever young, because it is forever burned. In that youth lies both beauty and terror. A world whose history cannot be read in scars, but only in flames. When most people imagine Io, they picture fire, fountains of lava, plumes of sulfur, a surface splashed in reds and yellows from endless volcanic activity. Yet beneath this blazing exterior lies one of Io's most intriguing mysteries: the possibility of an ocean. Not an ocean of water, like those on Europa or Enceladus, but an ocean of magma, a hidden sea of molten rock sloshing beneath the crust. It is a concept as strange as it is captivating. A world whose oceans are not blue and cool, but red and incandescent, forever roiling with liquid fire. The idea of a subsurface magma ocean on Io emerged from Galileo's observations in the late 1990s. Among its many instruments, Galileo carried a magnetometer, designed to measure magnetic fields around Jupiter and its moons. When the spacecraft flew close to Io, it detected something unexpected. The way Jupiter's immense magnetic field interacted with Io suggested the presence of an induced magnetic response inside the moon. Such a response requires a conductive layer beneath the surface. On Europa, a similar signature was interpreted as evidence of a global saltwater ocean. But Io is far too hot for water to remain stable. Instead, the conductivity pointed toward something else: molten silicate rock, perhaps forming a global magma ocean beneath the crust. Models developed from Galileo's data suggested that as much as 10 to 20% of Io's mantle might be partially molten, enough to form a continuous layer of magma extending across the globe. If true, Io is not just volcanically active on the surface, but internally oceanic, its fire not confined to eruptions, but flowing in vast subterranean seas. This idea aligns with the sheer scale of Io's volcanism. To sustain eruptions of the magnitude Galileo observed, an enormous reservoir of melt would be required. Something larger than isolated magma chambers, something global in scope. A magma ocean would also explain the persistence of Io's activity. On Earth, magma chambers eventually cool, eruptions subside, and volcanic provinces go dormant. On Io, eruptions are perpetual, with no sign of exhaustion. A global magma ocean would provide a continuous supply, a planet-wide reservoir feeding the hundreds of active volcanoes. It would be the engine of Io's eternal fire, replenished by tidal heating as the moon is stretched and squeezed by Jupiter's gravity. But what would such an ocean look like? Imagine beneath the crust, a layer of rock partially melted, forming a slurry of crystals and liquid. In some regions, the melt fraction might be high enough to behave like a true liquid ocean, convecting and churning under immense pressure. Above it, the crust would be thin in places, fractured by stress, allowing magma to surge upward in eruptions. Below it, the mantle would be hotter and more solid, slowly deforming under tidal stresses. The ocean, if it exists, would be a dynamic boundary, the place where tidal energy is most efficiently converted into heat, and where Io's internal life begins. The implications extend beyond Io. On Earth, geologists believe that early in our planet's history, after the giant impact that formed the moon, Earth itself may have possessed a global magma ocean. Over time, this ocean crystallized, releasing heat and gases, shaping the crust and atmosphere we know today. If Io has a magma ocean now, it offers a living analogue of Earth's fiery youth, a chance to study processes that shaped our own world billions of years ago, still ongoing in real time on a small moon around Jupiter. The possibility of liquid beneath Io's surface also sparks speculation about diversity. Could there be not only a magma ocean, but also a deeper silicate or even metallic ocean? Some models suggest Io's core is iron and iron sulfide, surrounded by a silicate mantle heated by tidal flexing. Between them may exist partially molten layers of varying composition. In this sense, Io is not simply a solid ball of rock with lava on the surface, but a stratified body with multiple liquid layers, each playing a role in its geologic symphony. Interestingly, Io may also conceal a connection to the icy moons. While Europa and Enceladus harbour oceans of water beneath ice, Io may represent the fiery counterpart, an ocean of rock beneath a thin, broken crust. The parallels are striking. In both cases, tidal heating drives circulation, creating global layers of liquid where none would otherwise exist. In both cases, the oceans define the moon's character, life-giving potential in one, fire-spreading energy in the other. Taken together, these moons illustrate the extremes of tidal energy, one producing water worlds, the other a furnace world. Of course, the evidence for Io's magma ocean is not ironclad. Some scientists argue that the magnetometer readings could be explained by highly conductive volcanic deposits or partial melts spread unevenly through the mantle, rather than a continuous global ocean. The exact melt fraction required for such conductivity remains debated. Yet even if Io does not host a perfect magma ocean, the idea captures something essential about its nature: that its interior is not static, but fluid, dynamic, and molten to an extraordinary degree. The presence of a magma ocean also raises profound questions about Io's long-term evolution. Can such an ocean persist indefinitely, or will it eventually cool and solidify, quieting the moon's fire? Tidal heating appears to be so efficient on Io that the magma ocean may be self-sustaining, its energy continually renewed by orbital resonance. As long as Io remains locked in its gravitational dance with Europa and Ganymede, its interior may remain molten, its surface forever reshaped. In this sense, Io's fate is not its own, but the product of celestial choreography. In popular imagination, oceans are symbols of life, of possibility. On Io, the ocean is one of fire, and its symbolism is different. It represents intensity, energy and renewal through destruction. Where Europa's hidden waters whisper of life, Io's hidden magma roars of violence. Yet both are oceans, reminders that liquid layers are central to planetary activity, whether water, ammonia, or molten rock. To explore the cosmos is to discover that oceans are everywhere, taking forms we never imagined, each with its own meaning. One day, future missions may test this idea more directly. A dedicated Io orbiter, equipped with improved magnetometers and heat-mapping instruments, could refine our understanding of its interior. Landers, though daunting in such a hostile environment, might analyze volcanic deposits for clues to the depth and composition of their source. In the meantime, Io's glowing hotspots, observed even by telescopes on Earth, serve as beacons of the fire beneath, hints of the oceanic inferno hidden below the crust. Ultimately, the possibility of an ocean beneath Io reminds us that extremes often come in pairs. Just as icy moons hide water oceans in the deep freeze, fiery Io may hide a magma ocean in the furnace of its interior. In both cases, energy from tidal heating transforms solid into liquid, creating global layers that defy expectation. Io's magma ocean, if it exists, is a reminder that the solar system is not simply a collection of frozen relics, but a place of living worlds. Some cold, some burning, all shaped by forces more powerful than we once dared to imagine. When we think of a moon's influence on its parent planet, we imagine tides, perhaps slight orbital tugs, or the faint gravitational pull of a satellite shaping rings. But Io is no ordinary moon. Its eruptions don't just transform its own surface. They spill into space, altering Jupiter's entire magnetic environment. Io is not simply a world of fire in isolation. It is the beating heart of a system of plasma and energy that envelops the largest planet in the solar system. To understand Jupiter's magnetosphere, one must understand Io. Jupiter's magnetic field is colossal, the strongest of any planet, extending millions of kilometers into space. Within this invisible cage, charged particles whirl at near-light speeds, forming belts of radiation so intense they would fry electronics and flesh alike. Into this maelstrom of magnetism, Io continuously injects matter. Every eruption, every volcanic plume, releases gases into Io's thin atmosphere: sulfur dioxide, sodium, potassium, and other compounds. Much of this material does not remain bound to the Moon. Jupiter's magnetic field strips it away, ionizes it, and traps it in orbit around the planet. The result is the Io plasma torus, a donut-shaped ring of sulfur and oxygen ions encircling Jupiter along Io's orbit. This plasma torus is immense. Billions of kilograms of material stream into it every second, supplied directly by Io's volcanic breath. Instead of being swallowed quietly, this material becomes electrified, spiraling along magnetic field lines, glowing in ultraviolet light. From afar, with the right instruments, the plasma torus is visible as a luminous halo, a cosmic neon sign announcing Io's presence. Few moons in the solar system influence their planets in such a dramatic and measurable way. Io is, quite literally, pumping Jupiter's magnetosphere full of plasma. The consequences are spectacular. As charged particles from the torus race along Jupiter's magnetic field lines, they plunge into the planet's poles, igniting auroras far more powerful than Earth's northern and southern lights. Telescopes like the Hubble Space Telescope have captured these auroras glowing in ultraviolet, shimmering with energy 100 times stronger than anything seen on Earth. Remarkably, some of these auroral features can be traced directly back to Io. Its interaction with the magnetosphere creates a footprint, a glowing spot in Jupiter's aurora that corresponds to the Moon's orbital path. Io leaves a luminous trail across Jupiter's poles, a direct signature of the electromagnetic bond between planet and Moon. The electromagnetic connection between Io and Jupiter is not merely beautiful. It is powerful. Io acts as a unipolar inductor, generating enormous electric currents as it moves through Jupiter's magnetic field. These currents can reach millions of amperes, dwarfing the largest power plants on Earth. They flow along magnetic field lines, linking Io to Jupiter's atmosphere in a circuit of energy that spans hundreds of thousands of kilometers. In a sense, Io is not only a volcanic world, but also an electric generator, a dynamo in orbit. This constant flow of plasma and energy has profound effects on Io itself. The stripping of its atmosphere means Io is perpetually losing material, its volcanic gases torn away as quickly as they are released. Its surface, already tortured by eruptions, is also bombarded by energetic particles from Jupiter's radiation belts, sputtering away atoms and coating the Moon with exotic deposits. To orbit so close to Jupiter is to live under assault. Gravitationally needed, volcanically tormented, and magnetically scourged. Io is both a victim and a participant, a moon punished by its planet yet inseparable from its system. For Jupiter, Io is both a source of fuel and complexity. The plasma torus alters the structure of the magnetosphere, creating currents and waves that ripple outward. These disturbances can affect the dynamics of Jupiter's radiation belts, the intensity of its auroras, and even the way the magnetosphere interacts with the solar wind. In effect, Io ensures that Jupiter's magnetic environment is not just a planetary shield, but a system shaped by moon-planet interaction. Few other planetary systems in the solar system demonstrate such a close and dramatic relationship. This relationship has implications far beyond Jupiter. For astrophysicists, Io and its plasma torus provide a natural laboratory for studying how moons interact with giant planets. Similar processes may occur in exoplanetary systems, where moons, orbiting close to gas giants could feed plasma into magnetospheres, generating auroras visible from across interstellar distances. Observing Io helps us imagine what we might one day see around distant worlds. Glowing signatures of moons caught in magnetic webs. Io's plasma torus also connects back to its volcanism in a feedback loop. The more Io erupts, the more plasma fills Jupiter's magnetosphere. The more plasma, the stronger the auroras, the brighter the signature. This means that Io's activity is not confined to its own surface, but resonates outward, written in light on Jupiter's poles. The moon's internal fire, born of tidal heating, literally paints patterns in its planet's atmosphere. Yet, for all its grandeur, this relationship is also destructive. Io's constant loss of material means it is being whittled away, atom by atom. Over geological timescales, the volcanic gases that escape into space represent a steady erosion of the moon's mass. It is unlikely to disappear entirely, of course. Its size and gravitational bond to Jupiter ensure its survival. But it lives in a state of perpetual loss, bleeding its atmosphere into the void. To orbit Jupiter is to be part of something larger than oneself. Io demonstrates this with a clarity unmatched by any other moon. Its volcanoes are not isolated phenomena, but the sources of a planetary-scale electrical and magnetic system. Its eruptions echo in the auroras of Jupiter, its atmosphere mingles with the planet's magnetosphere, and its plasma torus hums with the energy of millions of amperes of current. Io is at once a world unto itself and a vital organ in the body of the Jovian system. For scientists and explorers, this makes Io invaluable. By studying it, we learn not only about volcanism and tidal heating, but also about plasma physics, magnetospheric dynamics, and moon-planet interactions. Io is a nexus of disciplines, a reminder that planetary science is not only about geology, but also about electricity, magnetism, and the dance of charged particles across space. The vision of Io is therefore twofold. On the surface, it is hell. Lava lakes, sulfur plains, mountains blackened by fire. But above in space, it is also beauty, glowing auroras, luminous plasma, electric currents flowing invisibly between planet and moon. Io is destruction and creation, torment and connection, a hell that writes its presence in light across the sky of Jupiter. For all its violence and strangeness, Io is more than a spectacle. It is a teacher. This tortured moon, forever remade in fire, has become a natural laboratory for one of the most profound lessons in planetary science. That worlds are not shaped only by their size or their distance from the sun, but by the hidden forces of energy transfer. Io shows us how gravitational tides can forge volcanoes, how orbital resonances can sustain activity for billions of years, and how planetary energy comes in many forms beyond the familiar. On Earth, our planet's energy is powered largely by two sources: residual heat from formation and radioactive decay deep in the mantle. This energy drives plate tectonics, builds mountains, and fuels volcanoes. Mars, smaller and less endowed, cooled faster and grew quiet. The moon, too, is geologically dead, its energy spent. By contrast, Io, smaller than our own moon, should by all accounts be equally cold and inert. And yet, it blazes with activity. Why? Because Io's true power source is not internal, but external, the relentless tug of Jupiter's gravity. Tidal heating, the process by which Io is kneaded like dough as it orbits Jupiter, demonstrates the potency of gravitational energy. Every orbit, Io is stretched and compressed as its elliptical path brings it closer and farther from the giant planet. This constant flexing generates friction in the interior, releasing heat. The resonance with Europa and Ganymede ensures that Io's orbit never circularizes. locking it in a cycle of stress that cannot end. The result is astonishing. More heat per square meter than Earth, eruptions hotter than any recorded on our planet, and a surface in perpetual renewal. Io proves that tidal heating is not a minor curiosity, but a force powerful enough to dominate an entire world. This lesson reverberates across the solar system. Europa and Enceladus, while not volcanic infernos, owe their subsurface oceans to the same process. In them, tidal heating manifests not as fire, but as liquid water, kept from freezing by internal warmth. Where Io's energy erupts as lava fountains, Europa's emerges as cracks in ice, and Enceladus's as geysers of vapor. The diversity of these outcomes underscores the versatility of tidal heating. Depending on composition and context, it can create fire, water, or something in between. Io teaches us that the same physical principle can yield wildly different worlds, each habitable in its own way. Habitable to microbes in icy oceans, or habitable to the imagination in seas of fire. The significance extends beyond our solar system. Astronomers have now detected thousands of exoplanets, some orbiting close to their stars, others locked in resonances with companions. Many of these worlds may experience tidal heating on scales equal to or greater than Io. Some exomoons, orbiting gas giants around distant suns, could be Io-like volcanically active bodies, glowing in infrared with constant eruptions. Others might resemble Europa, with oceans beneath ice. In both cases, the principle remains. Tidal energy is universal, shaping worlds wherever resonance and gravity conspire. Io is our closest, most vivid example of what such energy can do. Io also teaches us about the balance of energy and habitability. We tend to equate habitability with liquid water, moderate temperatures, and Earth-like conditions. But Io reminds us that too much energy can be as limiting as too little. Its surface, dominated by sulfur and molten rock, is almost certainly hostile to life. Yet its very extremity helps us define the boundaries of possibility. If Europa represents the promise of life, Io represents the opposite. A world where energy has run wild, turning habitability into inferno. Together, these moons frame the spectrum of tidal outcomes, teaching us that not every active world is a living one. There is also a philosophical lesson. Io reminds us that planetary science is not only about static snapshots, but about dynamic processes. Most worlds show us their past. Mars, with its ancient riverbeds, the Moon, with its craters. Io shows us the present. It is not a fossil, but a performance. Its eruptions happen now, reshaping landscapes as we watch. To study Io is to witness geology in real time, to see planetary energy unleashed not as an abstract principle, but as a living force. It is a reminder that the solar system is not dead, but alive with motion, fire, and change. And Io's reach extends beyond itself. Its eruptions do not end at the surface but feed Jupiter's magnetosphere, creating plasma toruses, auroral footprints, and electromagnetic currents. This too is a lesson. The planetary energy is not confined within crusts and mantles, but radiates outward, shaping entire systems. Io demonstrates that moons can sculpt their planets as much as planets shape their moons. It is a world of feedback loops, where volcanism fuels magnetism, and magnetism in turn shapes space weather around Jupiter. Io also challenges our understanding of planetary interiors. The evidence for a global magma ocean beneath its crust forces us to reconsider how heat is stored and moved within small bodies. It suggests that oceans, whether of water or rock, may be common features of planetary evolution. Earth's magma ocean has long since solidified, leaving only hints in the geological record. Io's may exist now, a living analogue of conditions that shaped our world in its infancy. To explore Io is to glimpse the fiery cradle of planets, preserved not in rock strata but in present reality. For future exploration, Io stands as both an opportunity and a challenge. Its activity makes it compelling, a laboratory of volcanism, energy, and plasma physics. Yet its hostility makes it forbidding. Radiation from Jupiter's belts bombards it constantly, making prolonged missions difficult. Its eruptions are unpredictable, its surface volatile. But the rewards of studying it up close, mapping its lava flows, measuring its heat flux, probing its magnetic response, would be profound. I would reveal not only itself, but the deeper truths of planetary energy across the cosmos. In the end, what Io teaches us is that energy is the sculptor of worlds. Gravity, resonance, and orbital mechanics can combine to forge extremes that defy intuition. Small moons can burn brighter than planets. Eruptions can reshape surfaces in years, and plasma can link moons to planets in circuits of electricity. Io is the demonstration of these truths, a living experiment written in fire and sulfur. To look at Io is to see planetary energy at its most raw and untamed. It is not life-giving, not gentle, not Earth-like. It is violent, relentless, and overwhelming. And yet in its violence lies clarity, the lesson that energy, in whatever form it takes, is the driver of planetary destiny. Io is hell in the heavens, but it is also a teacher. And the knowledge it offers reshapes not only our understanding of moons and planets, but of worlds across the universe. Ganymede and Callisto, the giants. Among the more than 200 moons orbiting planets in our solar system, one stands apart as the undisputed monarch. Ganymede, the third of Jupiter's 4 great Galilean moons, is the largest moon in the solar system. A world so immense, it outstrips the planet Mercury in diameter. With a width of over 5,200 kilometers, Ganymede would be classified as a planet in its own right, were it not bound to Jupiter's gravity. To describe it merely as a moon is to undersell its grandeur. It is a planet-sized world orbiting a planet, complete with its own complex geology, layered interior, and even a magnetic field. In many ways, Ganymede is the closest thing to a hybrid between a moon and a planet, straddling the boundary between satellite and sovereign. The scale of Ganymede is the first feature that demands attention. Standing on its icy surface, if such a thing were possible, the horizon would curve away much like it does on Earth, and its bulk would be impossible to mistake for anything small or secondary. Despite its size, however, Ganymede's mass is only about half that of Mercury, because it is composed largely of water ice mixed with rock. This combination makes Ganymede a transitional object, neither a purely rocky terrestrial planet, nor a simple icy moon. Instead, it is layered like Earth, with an iron-nickel core, a silicate mantle, and an icy crust hundreds of kilometers thick. Beneath that ice may lie a hidden ocean, a reservoir of liquid water that rivals or even exceeds Earth's seas in volume. Ganymede is, in every sense, a world, not a mere companion. But what truly makes Ganymede unique is its magnetic field. It is the only moon in the solar system to generate one. This is not simply an induced magnetic response like that seen on Europa or Callisto, where subsurface oceans conduct electricity and interact with Jupiter's magnetic influence. No, Ganymede possesses a true intrinsic magnetic field, born from the motions of liquid iron in its core. Like Earth, Ganymede is a dynamo, its core stirring and spinning, producing a shield of magnetism around itself. This discovery, made by NASA's Galileo spacecraft in the 1990s, astonished scientists. Before then, no one had imagined that a moon could generate its own magnetic field. It was a sign that Ganymede was not simply large, but internally active in a way that blurred the lines between planet and moon. This magnetic field has dramatic consequences. It interacts constantly with Jupiter's immense magnetosphere, the largest magnetic environment in the solar system. Ganymede orbits deep within it. But rather than being swept helplessly along, it carves out its own miniature magnetic bubble. This bubble, known as a magnetosphere within a magnetosphere, is unlike anything else we know. At the poles of Ganymede, auroras shimmer as particles spiral along magnetic field lines, just as they do on Earth. The Hubble Space Telescope has even captured these auroral ovals, shifting slightly back and forth, oscillating under Jupiter's influence. These tiny wobbles were later used as evidence of a subsurface ocean, which dampens the motion of the auroras through electrical conductivity. In this way, Ganymede's magnetic field has become a tool for peering inside it, revealing the layered secrets beneath the ice. To grasp the significance of this magnetic field, one must remember that even Mercury, a planet orbiting closest to the Sun, has only the faintest whisper of a field. Mars, larger than Ganymede, lost its dynamo billions of years ago. That a moon, orbiting far from the Sun, bound to Jupiter's will, can generate a robust planet-like magnetic field challenges assumptions about planetary energy. It suggests that size alone does not determine vitality. Composition and history play equally important roles. Ganymede, with its iron-rich core and layered structure, holds onto a dynamo where larger worlds have gone silent. In doing so, it demonstrates that moons can be as complex as planets, worthy of study not as appendages, but as independent worlds. The existence of a magnetic field also raises questions about habitability. While Ganymede's radiation environment is harsh, its field provides some measure of shielding, reducing the impact of Jupiter's lethal radiation belts. This makes Ganymede a more hospitable environment for potential subsurface life than Europa, which is bombarded relentlessly. If an ocean lies beneath Ganymede's ice, as evidence increasingly suggests, it may be partially protected by the combined effects of the ice shell and the magnetic field. In this sense, Ganymede is not only a geological marvel, but an astrobiological candidate, a place where conditions might support biology in the darkness below. Culturally and symbolically, Ganymede has always loomed large. Discovered by Galileo Galilei in January 1610, along with Io, Europa and Callisto, Ganymede helped prove that not everything in the heavens orbited Earth. Its discovery was part of the revolution that shifted humanity's worldview from geocentric to heliocentric. Even then, early observers marveled at its size, noting that it was far larger than Earth's moon. In mythology, Ganymede was the beautiful Trojan youth abducted by Zeus, Jupiter, to serve as cupbearer to the gods, a tale of being chosen and elevated. In planetary science, the moon that bears his name reflects that story. A satellite elevated by its size and complexity to near-planetary status. What Galileo the spacecraft revealed centuries later only heightened this sense of grandeur. Images showed a patchwork surface, bright grooved terrain carved by tectonic processes, dark ancient regions scarred with craters and polar caps coated with frost. The magnetic field added another dimension, transforming Ganymede from merely large to dynamically alive. This duality, a massive body with a fossil surface in some regions, but active processes hidden in its interior, makes Ganymede one of the most intriguing objects in the solar system. From a scientific perspective, Ganymede offers a crucial test case. Its size allows it to differentiate like a planet, forming a metallic core. Its magnetic field proves it remains geologically active at depth. Its icy crust and potential ocean connect it to the family of ocean worlds, bridging the gap between Europa's active ice shell and Callisto's ancient silence. In many ways, Ganymede embodies all possibilities. It is a planet-sized moon with a planetary dynamo, an icy ocean, tectonic processes, and a surface that records both activity and ancient history. It is not only the king of moons by size, but also by complexity. Perhaps most tantalizing is the sense of scale it gives us. If Ganymede orbited the Sun alone, it would be classified as a planet. It has the size, the differentiation, and the magnetic field. That it orbits Jupiter instead shows us how arbitrary our definitions can be. Worlds are worlds, whether they orbit planets or stars. Ganymede's existence reminds us that the solar system is more diverse than simple categories suggest, and that moons can rival planets in majesty. In the grand theatre of the Jovian system, Ganymede is the sovereign, the king among moons. Its sheer bulk commands attention, its magnetic field speaks of hidden strength, and its layered structure suggests mysteries still to be unraveled. It is a world that bridges categories, challenges assumptions, and expands our sense of what moons can be. To study Ganymede is to study a planet in all but name, one that reigns quietly under the shadow of Jupiter, but stands alone as a world worthy of its crown. If Ganymede's size and magnetic field make it majestic, its surface makes it mysterious. When Voyager 1 and 2 first swept past Jupiter in 1979, their cameras revealed something unprecedented. Vast swaths of terrain, crisscrossed by long parallel grooves and ridges, cutting across older, darker landscapes. These were not simple cracks or fault lines, nor were they volcanic flows in the style of Io. Instead, they looked like the scars of some immense tectonic upheaval, stretching for thousands of kilometers. No other body in the solar system bore such features. Scientists quickly realized that Ganymede's grooved terrain was not only unique, but central to understanding the moon's history, and possibly its interior life. Ganymede's surface is a patchwork of two main types of terrain. Roughly a third is covered by dark, heavily cratered regions, thought to be ancient and relatively unaltered since the early days of the solar system. The rest is made up of the grooved terrain, lighter in color, less cratered, and clearly younger. These grooved regions consist of parallel ridges, troughs, and bands of ice that run for hundreds or even thousands of kilometers, often intersecting in complex patterns. In places, the grooves are several kilometers wide and hundreds of meters deep, like frozen scars carved into the crust. What caused this bizarre geology? One hypothesis is that the grooves are the result of tectonic processes, similar in some respects to those on Earth. Unlike our planet, Ganymede lacks plate tectonics as we know them, but its ice shell may have shifted and stretched under internal stresses. As the icy crust fractured, material from below may have welled up and refrozen, creating ridges. Some regions look as if great slabs of crust were pulled apart, rotated and slotted back in at new angles. In this sense, Ganymede may have undergone an era of icy tectonics, driven not by mantle convection like Earth's plates, but by the stresses of tidal heating and the slow cooling of its interior. Another possibility is that cryovolcanism played a role. Cryovolcanism, volcanic activity involving water and other volatiles instead of molten rock, is thought to shape many icy moons. On Ganymede, liquid water or slushy ice from a subsurface ocean may have erupted through fractures, flooding the surface before freezing solid. These flows could have resurfaced regions and created ridged patterns as they cooled and contracted. The bright, reflective nature of the grooved terrain supports this idea, as it suggests relatively fresh ice compared to the darker, weathered ancient crust. The grooved terrain also shows signs of compression and extension, implying a complex history of stress and release. In some areas, the grooves are arranged in parallel sets, as though the crust had been stretched. In others, they form polygonal networks, suggesting that the surface was compressed and fractured in multiple directions. Some scientists propose that Ganymede once expanded slightly, its interior warming and causing the ice shell to stretch outward. Later, as the interior cooled, contraction may have followed, creating additional stress. The grooved terrain thus records cycles of geological upheaval, a frozen archive of forces that reshaped the Moon over time. Galileo's close observations in the 1990s deepened the mystery. High-resolution images revealed intricate details. Ridges composed of twin bands, separated by a central trough, surfaces scarred by smaller cracks and faults, and evidence of icy flows that smoothed over older craters. In some places, the grooves appear layered, as though multiple episodes of resurfacing occurred. Galileo also showed that the grooved terrain is not uniform. It varies across the globe, with some regions showing dense networks of ridges and others more isolated bands. This suggests that the processes creating the grooves were not global but regional, influenced by local conditions in the ice shell and interior. What makes the grooved terrain especially intriguing is its age. By counting craters, scientists estimate that it formed between 1 and 4 billion years ago, much younger than the dark, ancient regions. This means that Ganymede underwent a dramatic geological transformation in its middle age, resurfacing vast areas in an episode or episodes of intense activity. Why this happened remains uncertain. Some suggest that orbital resonances with Europa and Io may have increased tidal heating during certain epochs, softening Ganymede's interior and driving tectonic shifts. Others argue that internal differentiation, the separation of ice, rock, and metal into layers, could have released enough energy to fracture the crust. The scale of this activity is breathtaking. Some grooved bands are thousands of kilometers long, rivaling the size of continents on Earth. To create them, immense forces must have acted on the crust, forces capable of stretching and breaking ice as thick as tens of kilometers. These grooves are not small features. They are planetary-scale scars, testimony to Ganymede's internal power. That a moon, even one as large as Ganymede, could undergo such upheavals challenges the old notion of moons as passive and inert. In recent years, the grooved terrain has also become a key clue in the search for Ganymede's subsurface ocean. If liquid water exists beneath the crust, it could weaken the ice above, making it easier to fracture and shift. The presence of grooved terrain, therefore, may indirectly support the case for an ocean. Furthermore, the conductivity detected in Ganymede's magnetic field, evidence of a salty liquid layer, aligns with the idea that the grooved regions are surface expressions of activity linked to that ocean. In this way, the grooves are not just geological oddities, but windows into the moon's hidden depths. Comparisons with other moons highlight Ganymede's uniqueness. Europa, for example, also shows ridges and bands, but its surface is much younger and more active, with cracks constantly opening and shifting. Callisto, by contrast, is heavily cratered and shows little evidence of tectonic activity. Ganymede sits between them. More dynamic than Callisto, but less so than Europa, a moon that experienced great upheavals in the past, but has since quieted. The grooved terrain is the frozen record of that upheaval, a reminder of a time when Ganymede's interior was restless. To planetary scientists, Ganymede's grooved terrain poses both a challenge and a promise. The challenge lies in its ambiguity. No single theory fully explains it, and likely multiple processes work together. The promise lies in what it represents. evidence that icy worlds can be tectonically complex, reshaping themselves in ways that rival rocky planets. If Ganymede could generate such terrain, then other large icy bodies, from Saturn's moons to distant Kuiper Belt objects, may also hold surprises. Culturally, the grooves enhance Ganymede's mystique. They make its surface look artificial in some images, as though carved by deliberate design. Of course, they are natural, but their scale and orderliness invite comparison to architecture, planetary freeways, the scaffolding of a world. They remind us that nature, left to its own devices, can create patterns as intricate and striking as any made by human hands. In the end, Ganymede's grooved terrain is not just a geological curiosity, but a story. It tells of a world that was once torn and remade, of stresses that fractured its crust and reshaped its face. It speaks of oceans below, of tides and heat, of forces that ripple through icy worlds as powerfully as through rocky planets. Above all, it reminds us that moons are not dead rocks orbiting giants, but worlds in their own right, with histories written in scars and grooves across their surfaces. If Ganymede is the king of moons, active and magnetic, then Callisto is the elder, silent, scarred, and ancient. Orbiting farther from Jupiter than its siblings, Callisto has escaped much of the gravitational torment that shapes Io and Europa, and even the tectonic convulsions of Ganymede. Instead, Callisto has remained largely still for billions of years, preserving on its face a record of impacts stretching back to the birth of the solar system. Where Ganymede is dynamic, Callisto is conservative. Where Europa hides its secrets beneath ice, Callisto displays them openly, like a fossil record carved into stone. From the first images captured by Voyager in 1979, scientists realized Callisto was a world unlike the others. Its entire surface is heavily cratered, with no smooth plains, few signs of tectonics, and almost no evidence of volcanic activity. In planetary science, such a surface is called saturated, meaning that every new crater overlaps an older one. It is as though the moon has been frozen in time since the era of heavy bombardment more than 4 billion years ago. In this sense, Callisto is not just a moon, but a time capsule, its surface a museum of cosmic collisions. Among Callisto's most striking features are its enormous impact basins, vast circular scars that dominate the landscape. Chief among these is Valhalla, the largest multi-ring structure in the solar system. Spanning nearly 4,000 kilometers, Valhalla consists of a central bright region, surrounded by concentric rings that ripple outward like waves frozen in ice. To gaze upon it is to imagine the violence of the impact that formed it, an object many tens of kilometers across slamming into Callisto and sending shock waves reverberating through the crust. Unlike on Earth, where erosion and tectonics erase such scars, on Callisto the wound remains, preserved for eons. Another colossal basin is Asgard, slightly smaller but equally impressive, also surrounded by concentric rings. Together, Valhalla and Asgard stand as monuments to the cataclysmic bombardments of the early solar system. They remind us that the outer planets and their moons were not spared from the cosmic violence that shaped Mercury, Mars, and the Moon. In fact, Callisto may preserve the best record of this era, because it has remained so geologically quiet. Where Ganymede's grooves and Europa's resurfacing erased parts of their history, Callisto's silence has allowed it to endure. This silence is not simply a matter of luck. Callisto's distance from Jupiter, nearly 2 million kilometers farther out than Ganymede, means it experiences far less tidal heating. It is not locked in the same orbital resonance that drives Io's volcanism and Europa's icy shifts. Without constant gravitational kneading, Callisto's interior has cooled and stabilized. There are no great stresses to crack its crust, No subsurface activity to push up fresh ice. No tectonic plates sliding past each other. Its surface is, geologically speaking, static. The bombardments of the early solar system left their marks, and nothing since has been powerful enough to erase them. And yet, for all its apparent stillness, Callisto is not entirely simple. Galileo's flybys in the 1990s revealed subtle variations in terrain. The bright frost that covers some crater rims suggests occasional resurfacing by small-scale processes, perhaps thin frost deposition or sublimation. Some regions show signs of icy flow, where slushy material may have crept across the surface long ago. And magnetic data hinted at the possibility of a subsurface ocean, much like those suspected on Europa and Ganymede. If such an ocean exists, it lies far beneath the crust, insulated by tens or even hundreds of kilometers of ice. Unlike Europa's relatively thin shell, Callisto's ice would make direct interaction with the surface unlikely. Still, the possibility adds a new layer of intrigue to a world once thought utterly dead. What sets Callisto apart is its role as a fossil record. Planetary scientists often long for surfaces that preserve ancient history. Earth constantly recycles its crust. Mars has lost much of its earliest record to erosion and volcanism. Even the Moon, though heavily cratered, has regions resurfaced by lava. Callisto, by contrast, is almost purely ancient. Its craters span every scale, from tiny pits to massive basins, each one layering atop the other in a tapestry of collisions. By studying Callisto, we can reconstruct the impact history of the outer solar system, gaining insights into how planets and moons were bombarded during their formative years. The sheer density of craters also changes our perception of beauty. Callisto's surface lacks the dramatic grooves of Ganymede or the striking fractures of Europa. Instead, its beauty lies in its complexity, in the sheer abundance of overlapping structures. To look at Callisto is to see an encyclopedia written in craters, each one a chapter in a story billions of years long. The largest basins are like epic sagas, the smaller craters like footnotes, but together they form a coherent whole, the geological biography of a moon that has endured. Callisto's ancient surface also carries philosophical weight. It reminds us that stillness has value. Where Io dazzles with its eruptions and Europa tempts with its oceans, Callisto teaches patience. It shows us what happens when a world avoids extremes, when it sits quietly at the edge of a giant planet's influence. In its quiet, it preserves truths that more active worlds erase. In its scars, it holds memories of a time before Earth's continents existed, before life arose, before the solar system settled into relative calm. Callisto is not just a moon, it is an archive. The presence of a potential ocean beneath all this quiet adds a paradox. Could a world so seemingly dead on the surface harbor liquid water within? Could life, however primitive, exist in the deep, hidden away, beneath ice that has not cracked for eons? While the prospects are less promising than on Europa, the idea cannot be ruled out. If true, it would mean that even the most ancient and static moons can conceal surprises. The juxtaposition of a fossil surface and a living ocean beneath is one of the great mysteries awaiting future missions. For explorers, Callisto may also be one of the most practical of Jupiter's moons. Its distance from Jupiter shields it from the intense radiation that makes Europa and Io so hazardous. A base on Callisto's surface would be far safer than on its siblings, with a relatively benign environment, compared to the hellish inner moons. Some have even proposed Callisto as a staging ground for future human missions to the Jovian system, a quiet outpost from which to study the more active worlds nearby. In this sense, Callisto's silence may one day serve humanity's voice in exploration. In the grand symphony of Jupiter's moons, Callisto is the bass note, steady and enduring. Where Io shrieks in volcanic fury, and Europa whispers of hidden seas, Callisto hums with the resonance of deep time. Its surface is not dramatic, but it is profound. It is the oldest, most complete record we have of what bombardment and stillness can do. And in that record lies a lesson that not all worlds must be active to matter, and that sometimes the most silent voices tell the oldest and truest stories. When we think of oceans in the outer solar system, our minds turn first to Europa, with its fractured ice and geysers, or to Enceladus, with its jets of vapor streaming into space. But beneath the silence of Jupiter's two largest moons, Ganymede and Callisto, there may also lie hidden seas. These are not seas we can see or measure directly, but oceans inferred from subtle clues, magnetic wobbles, density readings, and the strange behavior of auroras. If real, they transform both Ganymede and Callisto from static ice rock worlds into members of the growing family of ocean worlds and potential abodes of life. The strongest evidence came from the Galileo spacecraft in the 1990s. Galileo carried a magnetometer, a sensitive instrument for measuring magnetic fields. When the spacecraft flew by Ganymede and Callisto, it detected induced magnetic signatures that could not be explained by the moon's iron cores alone. At Ganymede, this was especially striking because the moon already has an intrinsic magnetic field of its own. Yet layered atop, it was a secondary signal, one that oscillated in step with Jupiter's rotating magnetosphere. The only plausible explanation was the presence of a conductive layer beneath the surface, a global ocean of salty water, capable of carrying electric currents and thus interacting with Jupiter's magnetic field. At Callisto, the case was more subtle, but still compelling. Unlike Ganymede, Callisto does not have a dynamo-generated field. But Galileo observed shifts in the external magnetic environment as the moon orbited Jupiter, consistent with the presence of a conductive ocean deep under the ice. The conclusion was astonishing. Not just Europa, but Ganymede and Callisto too, might harbor vast global reservoirs of liquid water, hidden far beneath their frozen shells. For Ganymede, the ocean is thought to lie between 100 and 150 kilometers below the surface, sandwiched between layers of ice. Models suggest it may be up to 100 kilometers deep, containing more water than all of Earth's oceans combined. This ocean may not be a single layer, but a stack of oceans, separated by high-pressure phases of ice. In this vision, Ganymede is a club sandwich world, ice crust on top, liquid water below, then more exotic forms of ice, and possibly additional liquid layers deeper still. At the very base, close to the silicate mantle, liquid water may again exist, warmed by contact with rock and enriched with minerals. This deep water layer, in particular, could be of astrobiological interest, because interaction with rock provides the chemistry needed for life. Callisto's ocean, if it exists, is likely buried even deeper. Estimates place it between 150 and 300 kilometers below the surface, insulated by a thick ice shell. Unlike Ganymede, which shows signs of past tectonic activity, Callisto's surface is geologically quiet, suggesting that if an ocean exists, it is not strongly interacting with the crust above. Still, the magnetic evidence is persuasive. Some form of conductive layer must lie below, and salty water remains the best candidate. Callisto's ocean may be more isolated, less active, and perhaps less hospitable to life than Europa's or Ganymede's, but it remains a profound possibility. That even the most ancient and cratered moon may conceal a hidden sea. The presence of these oceans has immense implications. First, it reinforces the idea that liquid water is common in the outer solar system. Once thought to be a rare commodity, water is now seen as abundant, locked in ice or flowing beneath crusts. with Europa, Enceladus, Titan, Ganymede, and Callisto all likely hosting oceans. The case grows stronger that oceans are not Earth's privilege, but a cosmic norm. Second, it widens the range of possible habitats for life. Even if the surfaces of Ganymede and Callisto are inhospitable, frozen, irradiated, or ancient, their interiors may be warm, liquid, and chemically rich. Astrobiologists are particularly interested in whether these oceans have contact with rock. On Earth, deep-sea hydrothermal vents provide energy and nutrients for ecosystems independent of sunlight. If Ganymede's deepest ocean touches the silicate mantle, similar vents could exist, releasing heat and minerals into the water. This would create conditions conducive to microbial life, even without sunlight. Callisto's ocean may be more isolated, but even there, chemical gradients between ice and water could fuel basic chemistry. While neither moon is as promising as Europa, both expand the spectrum of possibilities. The very thought of oceans beneath these giants changes their character. Ganymede is no longer just the king of moons with a magnetic field. It is also a water world, hiding seas more voluminous than Earth's. Callisto is no longer just a fossil of impacts. It may also be a paradoxical twin, ancient on the outside, liquid on the inside. They are not simply icy worlds, but hybrid ones, where rock, ice, and water coexist in layered complexity. Future missions will test these ideas. The JUICE spacecraft, Jupiter Icy Moons Explorer, launched by the European Space Agency in 2023, will spend years studying Ganymede, Europa, and Callisto. One of its primary goals is to probe Ganymede's ice shell and ocean using radar and magnetometers, confirming the depth, thickness, and structure of its liquid layers. JUICE will also fly past Callisto, gathering new data on its magnetic environment and surface composition. Together, these observations may confirm once and for all whether both moons belong to the roster of ocean worlds. Even with their hidden oceans, Ganymede and Callisto remind us of diversity. Europa's ocean interacts with a thin, fractured crust, creating spectacular surface features and geysers. Enceladus's ocean vents directly into space, offering a sample of its chemistry. Ganymede's and Callisto's oceans, by contrast, are buried deep, insulated beneath kilometers of ice, harder to reach, but vast in scale. They show us that oceans come in many forms: active, quiet, shallow, deep. And that habitability is not a single condition, but a spectrum. The thought of life in these hidden seas remains speculative, but it is not outlandish. Microbial organisms could thrive in dark oceans, feeding on chemical energy. If found, they would not only prove life exists beyond Earth, but also broaden our definition of habitable environments. If not found, the oceans would still be scientifically priceless, offering insights into planetary formation, chemistry, and energy transfer. Either way, the discovery that Ganymede and Callisto may harbor oceans reshapes our view of the solar system. Beneath the frozen crusts of these giant moons lies a reminder. Stillness at the surface does not mean silence within. Ganymede's grooved terrain and magnetic field already hint at hidden vitality, while Callisto's ancient face may mask a secret sea. In both, we see the paradox of the giants, worlds that look static but conceal depths of complexity, oceans of possibility waiting to be revealed. For centuries, Ganymede has been observed only through telescopes and fleeting spacecraft flybys, leaving more questions than answers. Now, for the first time in history, humanity has committed to sending a dedicated orbiter to this king of moons. The European Space Agency's JUICE mission, short for Jupiter Icy Moons Explorer, represents Europe's most ambitious planetary science mission to date, launched in April 2023. Its goal is nothing less than to unravel the mysteries of Jupiter's system, with a particular focus on Ganymede, the largest and most complex moon in the solar system. JUICE will not travel alone in spirit. NASA's Europa Clipper, launching later this decade, will concentrate on Europa, while JUICE will crown Ganymede as its primary destination. The two missions complement each other, forming a transatlantic partnership in the exploration of ocean worlds. But JUICE has a distinctive character. It is the first spacecraft ever designed to orbit a moon other than our own. That singular fact captures the historic nature of this mission. The spacecraft's journey is long. After its launch aboard an Ariane 5 rocket, JUICE is undertaking a series of gravity assists from Earth, Venus, and Mars to slingshot itself toward Jupiter. This trajectory, though indirect, saves enormous amounts of fuel and allows the spacecraft to arrive with enough energy to maneuver in the Jovian system. The cruise phase will last about 8 years, with arrival at Jupiter slated for the early 2030s. Patience is required, but the rewards promise to be extraordinary. Once at Jupiter, JUICE will perform flybys of the major moons, Callisto and Europa among them. But its ultimate goal is to enter orbit around Ganymede itself. This final orbital insertion will make history. Ganymede, larger than Mercury, will become the first non-planetary body other than Earth's moon to be orbited by a human spacecraft. For planetary science, this represents a shift in perspective. Moons are no longer side notes to planets, but worlds in their own right, deserving of dedicated missions. The mission's scientific goals are ambitious and wide-ranging. Chief among them is the investigation of Ganymede's subsurface ocean. Galileo's magnetometer data strongly suggested a conductive liquid layer beneath the ice shell, but the details remain elusive. How thick is the ice? How deep is the ocean? How salty is it? JUICE carries radar sounders designed to penetrate the icy crust, bouncing signals back from layers beneath. These instruments will map the internal structure, providing the most direct evidence yet of the ocean's presence and properties. Another key goal is to study Ganymede's magnetic field. As the only moon with its own intrinsic dynamo, Ganymede offers a natural laboratory for planetary magnetism. JUICE's magnetometers will measure the field in exquisite detail, disentangling the signals from its core, its ocean, and Jupiter's overwhelming magnetosphere. These measurements will not only tell us about Ganymede, but also about the nature of planetary dynamos in general. Why some worlds retain them, while others, like Mars, lose them. The surface of Ganymede will also come under close scrutiny. High-resolution cameras will map its diverse terrains, the ancient dark regions dense with craters, and the younger grooved terrains crisscrossed with ridges and troughs. By analyzing the distribution of these features, scientists hope to reconstruct the moon's geological history, its cycles of tectonics, resurfacing, and quiescence. Spectrometers aboard JUICE will analyze the surface composition, detecting salts, ices, and possible organic compounds. Together, these observations will illuminate the processes that shaped Ganymede's enigmatic face. Though Ganymede is the crown jewel, JUICE will not ignore Callisto. The spacecraft will perform multiple flybys of Jupiter's outer giant, gathering data on its ancient, cratered surface and magnetic environment. Callisto provides a crucial contrast to Ganymede, one moon geologically active in its past, the other seemingly frozen for billions of years. By comparing them, JUICE will help us understand why some moons evolve dynamically while others remain static. Europa too will receive attention, though JUICE will not fly as close as NASA's Europa Clipper. Still, its instruments will contribute to the search for surface chemistry, detecting water-related compounds and possible sites of exchange between surface and interior. Together, JUICE and Europa Clipper will form a dual narrative. One mission probing an active ocean world, the other an older, more complex one. The instruments aboard JUICE are cutting edge. The radar for Icy Moons Exploration, RIME, will probe Ganymede's ice shell to depths of up to 9 kilometers, mapping structures unseen before. The JMAG magnetometer will measure magnetic fields with high precision. The MAGIS spectrometer will capture light in infrared and visible wavelengths, identifying surface materials. Cameras and particle detectors will map terrain and monitor interactions with Jupiter's plasma. Altogether, JUICE carries 10 instruments, each chosen to address the great questions of habitability and planetary evolution. Why Ganymede? Because it embodies the convergence of scale, complexity, and habitability. It is the only moon with a magnetic field, the largest reservoir of water in the solar system, and a geological history that straddles activity and stillness. By orbiting Ganymede, JUICE will explore a world that is both planetary in scale and uniquely lunar in context. The mission aims not only to answer scientific questions, but to redefine our conception of moons as worlds. Symbolically, JUICE represents Europe's bold step into planetary exploration on a grand scale. While NASA has long dominated outer solar system missions, ESA's decision to focus on Ganymede demonstrates confidence, ambition, and vision. It acknowledges that the search for habitability and life beyond Earth is not the work of one nation, but a global endeavor. JUICE is Europe's flagship contribution to that effort, a spacecraft designed to ask questions as profound as they are practical. Can moons be habitable? How do magnetic fields arise? How do oceans survive beneath ice? For humanity, JUICE embodies the slow, patient arc of exploration. It will take a decade to arrive, years to orbit and study, and decades more for its data to be fully understood. By the time it completes its mission, some of those who watched its launch may be retired, others children grown into adults. Planetary exploration is not measured in months but in generations. JUICE is part of that continuum, a bridge between Voyager's flybys, Galileo's discoveries, and the future when perhaps landers or even submarines will one day probe Ganymede's ocean. The prospect of orbiting Ganymede invites us to imagine the view, looking down on vast grooved plains, watching auroras flicker at its poles, tracing ridges that stretch across hemispheres. It will be the first time we see such a moon, not in fleeting images, but in sustained detail, as a world studied up close. For the first time, Ganymede will cease to be a distant enigma and become, like the Moon and Mars, a world we truly know. In the end, JUICE is not only a mission to Ganymede, but a mission to ourselves, to our curiosity, our persistence, our willingness to invest decades in the pursuit of knowledge. It is a promise that we will not leave the outer solar system unexplored, that we will continue to seek answers in the cold and distant places. And in doing so, we may find not only oceans and magnetism, but a deeper sense of the diversity and wonder of worlds beyond Earth. When we speak of habitability in the solar system, our minds instinctively leap to Europa with its geysers, or Enceladus with its plumes of water vapor. But Ganymede and Callisto, though quieter, matter profoundly in this conversation. They may not flaunt their oceans openly, nor display the spectacular resurfacing of their smaller sibling, but they represent something equally essential: the diversity of habitable environments and the spectrum of possibilities for life. To understand them is to understand not only moons, but the very conditions under which biology might arise elsewhere in the universe. The first reason the giants matter is simple: scale. Ganymede and Callisto together contain more water than all the oceans on Earth, and then some. Even if only a fraction of that water remains liquid beneath their icy crusts, the sheer volume is staggering. When astrobiologists define habitability, the presence of liquid water is one of the fundamental criteria. By this measure alone, these moons become central to the discussion. They remind us that Earth is not uniquely water-rich. In fact, some of the largest water reservoirs in the solar system may lie hidden beneath the ice of distant moons. For Ganymede, habitability takes on a complex character. Its magnetic field sets it apart, shielding portions of its surface and ocean from Jupiter's deadly radiation environment. While the surface remains harsh and irradiated, the subsurface ocean could benefit from both the shielding of ice and the protective buffer of magnetism. Moreover, if the ocean contacts the rocky mantle deep below, as some models suggest, then it would have access to the minerals and chemical gradients that can power life. On Earth, hydrothermal vents at the bottom of our oceans teem with ecosystems independent of sunlight, fueled by chemistry alone. Ganymede's deepest layers may host similar energy sources, creating conditions where microbial life could, in theory, find a niche. Callisto represents the opposite pole. It lacks Ganymede's dynamism, its magnetic field, and its tectonic restlessness. Its surface is static, cratered, ancient, a fossil of impacts. And yet, it too may hide an ocean, albeit buried deeper and more isolated beneath a thick crust. Callisto teaches us that habitability does not have to be tied to visible activity. A world can appear dead on the surface but still sustain liquid water below. This expands our definition of habitable zones. Life may not require a constantly reshaping crust or dazzling geysers. It may simply require stability, water, and time. Callisto provides all three.